Welcome everybody to the second Phosphorus. It's really a pleasure to be here today. It was quite difficult to arrange everything this year. It was a really real challenge, right, Rafael? But I'm really glad that we are here again this year. I'll talk a little bit about, give a very short introduction about what we're going to have today. Last year, it was really great. I mean, it has been quite some time since the pandemic that we didn't have any kind of open source focused conferences in Brazil. So it was really nice for us to be able to organize Phosphorus here last year. We had very good feedback, number of interesting presentations. But yeah, I mean, this year, we are smaller, as you can see. But we still had 70 registrations, right? And we will have only one day. That's just because myself and Rafael, we didn't have time to organize something bigger with the sponsors or anything else that we would like. But, you know, we are here and we are really glad that we are here. The principles continue to be the same. So we want this to continue to be focused on free and open source hardware and software. We want it to be free to participate, right? Nobody's paying to be here. We want to have English as the main language. We still believe that training folks in Brazil to talk or speak in English and to listen presentations in English is very important. The world is completely connected. Bunch of people here, if they're not working for companies, foreign companies, they will be at some point in time. So it's important for us to train and to have this kind of event. And hopefully in the future, we will have, you know, foreign presenters as well. And that will help because, I mean, if we had presentations only in English, you know, that would make it even more difficult for them to participate and to interact with the others. I understand this is difficult for some folks, and I mean, this is a really, I mean, the way I see it is, you know, we are all kind of friends or we know each other, right? So it's a very understanding audience, right? So we're not asking anyone to have perfect English, of course. It's just a way of training and trying to, you know, expand your experience in this kind of
Welcome everybody
venue. Whoops.
to the second
I don't need
Phosphorus.
audio on this one, right? So, yeah, it's located in the university. We are the second time here at the Institute of Computing in UNICAP, and you're during a weekend, which is somewhat controversial with some folks. But yeah, we are still here in the weekend. So, code of conduct, I mean, just as last year, we don't have an explicit code of conduct. We believe that the laws in Brazil are extensively covering this. But if anyone has any issues, please just talk to myself or to Rafael, and we will promptly address any issues that you have during the conference, right? Data privacy, we are not going to share any information. You saw that, you know, unfortunately, for many reasons, we have to have a registration process in Brazil. So I had to ask your email and your name in order for you to attend. But yeah, that's all the information that we're going to collect. We don't plan to send a bunch of emails to you with marketing material, especially because we don't have sponsors this year anyway. So, you know, be sure that we are not going to share your information, and we will take photos. So if you have any problems with that, please let us know, because the Brazilian laws, I mean, we need to ask permission to do that kind of stuff. You know, even though we don't have sponsors, we do have some partners, and I would like to thank them. I mean, risc-v International, and I will let Rafael talk about this because I can't. So, Rafael.
Okay, so as part of risc-v
you need to stay here. Yeah.
It's the second time, so we are, as a no-profit organization, we can't offer a lot of money, but we can offer t-shirts. Thank you, Rafael, for the t-shirts. The other Rafael, to be honest. But yeah, risc-v International aims to share everything with me. Be present whenever we can. Share as much as possible the open source or the culture, along with the hardware, the open hardware, or the open standardized culture. And we are glad to be here. We are glad to be supporting this event, not just this event in Brazil, but others. Yeah, and we hope that next year we can make something bigger, and why not? In other place, bigger event. Maybe with sponsorships from companies like Mombrow Labs. We don't know. Anyway, I'm glad to be here again. So anything you can do to support risc-v in Brazil, we're going to be doing and we'll be participating. So thanks for being here.
Nice, thank you very much for you and risc-v International, of course. Linaro is the company that I work on, and they support the initiative. So, thanks for Linaro as well. Linaro is a company focused on developing software for ARM platforms and enhancing the reach and the quality of ARM platforms. Thanks for Unicamp and the Institute of Computing, because they are providing all the place, the venue, the infrastructure, really nice infrastructure that we are using so that we can stream the videos in the internet right now. And, we are recording the session so that others can watch them afterwards. And I would like to have a special thanks to ICTL as well. ICTL is the Instituto para a Conservação de Tecnologias Livres, very similar to the Software Freedom Conservancy, if I got the name right. It's a non-profit organization that helps open source and free software projects in Brazil to make events like this one, right? I mean, it's difficult to receive money or even to hold money from one year to another if you are just a conference. So there needs to be a legal phase for you. ICTL is this legal phase for a number of projects. So they support Debian Brazil, FOSForums, DebConf 2019 in Curitiba. They were the ones that organized that. They have also they've been also supporting FLUSP, the free software group at IME-USP, and they were also the supporters of Linux DevBR, which was an open source conference that happened in Brazil before the pandemic. If anyone is interested, I mean, they have a nice website with all the information about how they work and what you need to contribute with them. I would like to thanks again for a bunch of people. So Rafael, of course. Daniel Rodolfo, Professor Rodolfo, he is the one that is helping us to, have the space and all the infrastructure. I'd like to thank Andre. Andre is the guy here from the support that helped me with setting up everything yesterday, and Bruno is here today, and I don't have his photo because I wasn't aware who was going to be here today, but yeah, Bruno is helping as well. Daniel Barbosa was one of the early supporters of the conference. He is not able to be here today just because he has some work to do during the weekend. That happens.
He works on risc-v. That's fine. That's his work.
Yeah, he works for Ventana. And I would like to thank our speaker, so Carlos Mateus, who doesn't have a picture. Where's Mateus? Okay, so I hope this is some picture that you put somewhere, right, for you. Julio, Rafael, Desnis, Ellen, Gustavo Padovan is not speaking, but he also helped us to organize some stuff and helped us to get Ellen to speak about kernel CI from Collabora, Leonardo Braz, Charles, right? Charles. Antonio Terceiro and Daniel Lenharo, they are from ICTL. So thank you very much for all these folks. They helped us a lot in making this possible, even though, you see, we are a very small conference this year, but we still needed a lot of help to be here. So, yeah. This is the agenda for today. We have 8 presentations, coffee break at 10:40 or maybe 11 because we're a little bit late, lunch around 12:30 probably, and a coffee break in the evening, and we hope to be closing at 5 p.m. The agenda will stay in that monitor for the whole day. If you have any questions, please let us know.
For lunch, there is a restaurant down there.
You don't need to say that because I have a slide for that. So, this is where we are, right? This is the map of Unicamp. So you can see that we are over here at Institute of Computing. There is a restaurant over here at Unicamp, right? I think this is the one, right, yeah. Rafael? They are open today. If you want to go there, they have food because we said, we are going to have a conference nearby. So, if you want customers, you better have food on a Saturday. So they will open. There is also the university restaurant over here, which is called RS, right? If I understand correctly. And which is open now during the weekend. Last year they said that it wasn't, but this year it is. I'm pretty sure. So yeah, and there's a bunch of other restaurants over, nearby if you want to eat somewhere else.
No, that's it.
Okay, so that's it. Let's start with Carlos. And yeah, I hope everybody have a great day. Thank you very much. There you go.
Just see if I can flash the slides. Okay, the laser. Okay. So, good morning, everyone. First, I'd like to thank the organization board to the opportunity to be here. This is very important to me, and I'd like to thank for the Leonardo and Rafael. And so, let's start. I will talk about my recent experience in working with KiCad and open hardware. This was my first time, this project I will talk about. The idea is to talk about KiCad in this project that I made. The idea is to this project that I will talk about was my first project, making hardware and using KiCad. So it was my recent experience doing both. So the first thing, who I am. I'm Carlos. I'm undergraduate engineering student of the USP, the computer engineering student. And I consider myself as a FOSS advocate, and like Harold, as a really what I like open source. I think all the guys that are here also like. This is one of the things. And I think the main point is that I'm just a curious guy that likes to learn new things and loves to the experience of learning and doing new things. So yeah. So first thing, open hardware. For me, it was like a new experience. I learned I met the first time the open source culture. For the software part, so Linux kernel and all the things. So the new, exists, open hardware movement was very new thing to me. And the open hardware is like a very, the open hardware movement is also quite big and also very vast as the software part. You have open architectures, you have micro electronics, open hardware, a lot of things. But the main point today is talk about KiCad, and especially how the KiCad can help you to make good hardware and good things and incredible things. So, what was the incredible thing that I was making? So my original inspiration was this board. This, of course, this board is not mine. This is the inspiration. It is from a paper. I said it on in the end of the slides. My idea was to replicate this board. So, but the first question: why I want to make a board? Why I want to do this? What is this? Is the first question. So a little bit about story. I was helping a friend in my hometown. This my friend Edney was actually one of my physics teachers from the high school, and the guy that made a significant impact on my life. And I was helping him with the troubleshooting of some board. This board from the IFO 2017 is a Teslameter. I was making debugging the Teslameter. And I was discussing for him, and he called me and say, "Oh, I want to help with this." And also, I found an amazing article about a Bulgarian Olympiad in experimental physics, and they made a very good project that I want to bring to the students. So he asked me, "Could you make the board for me? Do you know how to do this?" And I said, "Oh, I never did it before. But I really want to try it." So this was the start. And the first question, what this board does? The board is intended to make an experiment to determine the Boltzmann constant. So the first thing is, what is the Boltzmann constant? And for this very short group of slides, I will ask you if you guys, that people that don't like much of physics, I will just make a very simple introduction just to explain the phenomena, because the whole point of the board is to determine the phenomena. And I think it was very important to make this short explanation. So the Boltzmann constant is one of the fundamental constants of the physics, and yeah, it's quite small, and it's for the educational purposes. It's very good to make constants and values of physics that seems like magic for the students. It's good to know how this exists. I can measure. This is the point of experimental physics. So this is the idea. Following the original article, it said that Einstein in 1902 proposed that in theory it was possible to determine the Boltzmann constant by evaluating the mean of the thermal energy. Just the main point. This was what Arjen proposed. The original article is in Deutsch. I don't speak Deutsch, so I am believing you what the people from the article said. But the original paper is available. The people who know Deutsch. But okay, the idea is to determine the Boltzmann constant by the means of the thermal energy. But how we can do this? To understand this, just to like see if a simple resistor, a simple component that you can like see, because of the random movement of the electrons, this resistor makes like you can see like a slight fluctuation in about of attovolts, and this fluctuation is known as thermal noise, and the thermal noise is like because of the movement of the electrons and is relating to the thermal energy. So the idea is to like measure the noise, but the mean of the noise is 0. How we can do this? We need to see the power of the signal, the power spectrumicity of the signal. So yes, looking at this, you guys don't need to know like the math of this, just to know is this the power of the signal. And looking with this, we see, oh, we have a value we can measure, and the most important thing is related to the Boltzmann constant. Einstein was right after all. But have some issues. The first issue is that, as I said, is in attovolts. This is nothing. We cannot measure this like taking a multimeter. It's not possible. And also we have dependency of the resistance and the frequency of the noise. The main point is that these things makes the experiment like unfeasible in this way. So the idea is like to put a capacitor, and with this, when you make the new PST of this signal, this voltage source, you can see that the mean square voltage that you see in the end is like dependent of the Boltzmann constant, is a bigger value, because using a small capacitor you can increase this to nanovolts, way better. But I will get the point when you can measure with a multimeter, but way better. And we like get out of the dependency of the frequency and the resistance. So very good. A capacitor is way well behaved than the resistor. So this is the main point. And for you guys, this is what I want to measure with the board. So the mean square voltage of this signal, just this thing. And this is the resistor. It's just divided in an ideal resistor in a voltage source. But yeah. And this is the original layout. So yeah, we are getting to the layout. We are closing to KiCad. This was the original layout proposed by the people from Sophia University. My idea was to replicate this thing. And for this, just explain this, the mean square voltage value is actually in nanovolts. It's quite small. This step here just amplifies this by 1,000,000 times. So we get from nanovolts to millivolts, a measure value, yeah. And in this part of the circuit, this here, just make the square part is a voltage multiplier, and in the end just a low pass filter for the guys who don't know electronics, but this take the average. So yeah, in the end we measure that thing, the mean square voltage of the signal. We can, with this, determine the Boltzmann constant. Okay, you guys understand the idea. So, okay, let's do the board. KiCad. KiCad is a cross-platform open source electronic design automation suite. I choose KiCad because my friends used KiCad to design some boards, and I want to try the software. And it's also very like beauty. It's very intuitive, and it's come close to like a professional tool. It's actually a professional tool to design circuits. It's close to Altium. Altium has more features, but for me, KiCad is like in the same level of Altium. So, okay, let's design a board with the KiCad. Design with KiCad, we get this like the intro screen, and we have a lot of features to access here. The first thing that we want to do when to make a board is the schematic part. So this was the original idea. But how we can do this in KiCad? The idea is like to open a blank canvas and start to placing the components in the correct way. You choose the component, choose the specification, see for example the fabrication that you want. You can like import some external symbols from the manufacturers and make your board. And this was my schematic. A lot of work to do. It's not like you jump from one to the other. And yeah, KiCad is a very powerful tool to do this. You can like make comments, draw the things, And also, one important thing, when you end your schematic, you need to check if it's right. It's right. So KiCad has a powerful ERC checker. This is like common in professional tools, and I would like to highlight this thing because the points that I will highlight in the presentation that make the KiCad, as I think, a professional tool to work with circuits. So you can, for example, check if you misconnect something, something is unconnected, something is short circuit. It's a very powerful tool. When you miss, you can configure the warnings, like the errors, the class of the error. And when you make a mistake, for example, this mistake here, it's a point here, explains, and if you click, they go right here and explain, oh, you short circuit this. You are sure that you want to do this, and you can, for example, no, I want to do this, and just disable the warning. But very powerful tool. This verification tool that I will talk in the presentation is the thing that makes is very important to professional design. So okay, this thing, and KiCad also has a simulation because we checked if we corrected things right, but it behaves the correct way. Simulation goes with this, and one of the things that KiCad is very good, and I think this is a recent feature, it was not available in the past versions, is like a native integration. You don't need to export like a SPICE model and simulate in the external simulator. It's integrated itself. I used KiCad version 7. Version 8 is way better, but I will discuss like issues with simulation at the end of the presentation. But this, for example, is an AC analysis of the gains part of the circuit. I have some issues determining like the simulation of the whole board, but I will get this on the later part. But for example, this is a working simulation of the amplifier circuit. So I could check, oh, it's behaving as expected. And for example, I was like with some like questions about the behavior, and I could like see in practice, oh no, yeah, it's working like this. If I change this, the simulation will like behave differently. So very good tool. And very professional. So okay, we made the schematic. We checked the components. We have like a working circuit in theory. How we can make it to like work in the real life. We need to make a layout. The layout is when you pick the schematic and oh, I want to place in a board that is actually manufacturable. So the KiCad has a layout part. You start with a blank canvas, and you guys can think, oh, I need to place the components all again. No, KiCad is going to help you. You can import the components from the schematic and you just click a button on there, on top, here. And you just can import all the components, just click update, and they are here. And it works like when you change, for example, something here on the schematic, you can just put in the layout like straightforward. It's not only on the start. So you can. The two of them are coupled. This is very interesting thing. So yeah, you put the components on their layout, just place them where you want, define the edge cuts of the board, put some pads, and yeah, you actually have a board. So with this, you can, for example, make a six string, like good things to put on the board, like some drawings, some explanations of what things are, and you can put all of this. With this in mind, you can, for example, start the routing process. That is like putting the wires, the tracks on the board. And for example, if you want, no, I want my power tracks way much wider than the signal ones. I want like I have a special connection. I want to make in a specific widths. How you can do this? So KiCad can like make classes. You can specify, oh, I want the power classes to be way wider, the standard ones in the specific way. You can change this, and with this set, you can just like route normally, and the KiCad will take the work to choose the correct width to the tracks. So very powerful, and just make the tracks. You have this like this board, and with all of this made, you can, for example, make the ground planes. It's very important to circuit design. With the ground planes correct draw in the board, you can, with this, you actually have a big capacitor because you have like a ground plane on top, a metal plate on the top, metal plate on the bottom, and a dielectric in the middle. For guys that know that electronics, this is a big capacitor. We don't want to do this. And to correct this, we can make like little short circuits on the board. This is known as V-stitching. And in the old days, you do this manually, so you can start put the V's, but this is like, no, this is not an engineer's job. This is like a technician job to do. And KiCad also has can get a hand with this, because they have nice KiCad add-ons that is like plugins for the KiCad. Because KiCad is scriptable. You can like make scripts, and you can share the scripts with the KiCad add-ons. So you can add, for example, new capabilities. For example, you can make KiCad to do like parasitic extraction. That is not so common, I think, for PCB designs, but for semiconductor like designs is very common. But you can implement this. Actually, KiCad has one of this. You can make like automation tools, as I will show here. And for example, you can share your 3D models, your symbols, all of this, and also share your color schemes. Why not put a Dracula scheme on the KiCad? You can't. You actually can. So okay, you go to the store. This was the old store. I think the KiCad 8 has like a way beauty store, but you choose your plugin. This is my installed plugins. The repository has 81 plugins. You choose this one, is the KiCad action scripts. And with this, just specify the parameters of your V stitching, the distance between them, the clearance, all the things, the pattern that you want to do, and it's done, actually. This is the V stitching thing made with the tool. Very, very fast, very powerful, and they generate like vias that are separate from the design. So if you have vias on your board, they will not interfere, and you can like, oh, I don't like this pattern, right? You just can erase the vias that generated and put it again. Very powerful tool, and this was one of the features that Altium has. People, oh, Altium is way better, but yeah, KiCad also has this feature. So very, very important. And this is the final board, actually. With this, we can make another checking part, very important to design, because the idea is to manufacture this board. So to manufacture, we need to like make it physical. To make it physical, someone needs to make the board, fabricate the board. And the manufacturer has some limitations, how thin the tracks can be, how small the holes can be, all the things. And to make, is my layout correct? You can have the DRC. DRC is like in the semiconductor part, the like microelectronics industry, it's way like more complex. In PCB, it's way simpler. The main points of the DRC is to check for geometric constraints. You don't like, it's not usual to check for parasitics and etc. But yeah, limitations on geometry, and also it also performs the DRC to check if you, for example, as I said, oh, I want to connect this part and that part with the circuit. And for example, I forgot for some reason. The DRC will warn me, oh, you not connected this. Are you sure it's correct? And for this, you can, for example, about the geometric constraints that I said, you can use an UI. It's very intuitive. We can just check, for example, the fabrication like website or datasheet, put the rules here, and you have like a DRC working. If you're, for example, your process is way more complicated, and you still want to use KiCad to do this, you can actually make, for example, custom rules, and that is not on the UI. So make custom rules. This is the GLC PCB custom rules. For example, they have like different rules for different layers, and you could just put this on your DRC, and it will work like straightforward. I not writing this on my own. The reference is on the GitHub. My GitHub repository is the where I found this code. It's for some guy on the GitHub, and yeah, you can do this, and their DRC will work. This is like an unconnection circuit. This is warning me, oh, missing connection between items. Very intuitive. This is like, I will emphasize this because some tools are, the error is not intuitive. They don't say, oh, an error, find yourself. They don't know, but this is saying, oh, is this thing unconnected? And very clear, very easy to work, very intuitive. And this, for example, is a constraint violation. They're saying the device is too small, and it's explained to me what's the error, how to correct, and the rule related to it. So very powerful. With this, all in mind, we checked out the things. We have a ready to go board, and but I want to see the board to see like previous to know to have an idea of my project before making to manufacture. You can use 3D visualization. That is, it supports ray tracing. It's very like beauty. I think it's better shown to than talk. And this was a 3D rendered by KiCad of my board. I have the board here. I forgot to bring the board here, but it's on my backpack. But yeah, this is the board, the 3D visualization. This is the board without the components. With the components, the back part, very beautiful, very like powerful tool, very professional, all the features. And yeah, I talked about KiCad, I talked about the project, and what the issues that I faced. Is KiCad perfect? No, actually don't. But it's a very good software, very powerful one. But I need to like make my complaints about it. The first complaint is that multi-project on KiCad is like painful because you need like to work with yourself the different projects, and if they relate to each other, you need to make the unity at your own. You need to manually put the things. KiCad could help with this. Altium has this capability. I don't know how why KiCad does not support this. I don't know, maybe, I don't know. Other thing was the simulation. On KiCad 7 it was like pretty worse. I would put more like complaints about it, but I checked in the version 8, that is the current version. They correct a lot of things, so the 7th version was not so great. The documentation, I think they are missing some things, but I'm saying the documentation is missing because the starting documentation is way good. It's like a very good tutorial, goes a lot of features on the project, and I'm just saying about the documentation because it's not that it's like horrible. It's because compared to other documentations, it's like missed some points, and I could be better. Actually, and other things. Even with KiCad 8, my whole simulation was not working, probably with some model issues. But I think it's like a limitation of the simulator, and this is not KiCad's fault. But I think, for example, supporting multiple backends could be good. But yeah, okay. Talk about a lot of things. Other thing was customization was a bit too laborious. We can't customize it, but okay, some issues. And okay, I talked about the issues. Future work is the last part of the presentation. The board arrived to me like yesterday, and I have the board here, but I was not expecting to have the boards as soon as this. But I need to check if it actually works in the real world. Also, I want to like reduce the cost, so some changes. But this is like the iterative design. I also check for design flaws. And other thing, this is very good for KiCad and FreeCAD in the like open hardware ecosystem is because you can actually integrate KiCad with FreeCAD and make like a mechanical and electrical like tool to work with both. And I want like to make a support board to my board, and I want to integrate the thing, but it's like future work, good thing to do. Very nice that they integrate itself, and yeah, make the simulation work. Why not in future work? So this is the reference, and this is the end of the presentation. Thank you very much for listening.
Any questions to Carlos?
You're bored.
Yeah.
Your board. I have a question. You said we're not expecting to have the board so soon. I mean, were you able to test and check?
No, it's arrived to me yesterday.
Okay. Yeah, because I'm just curious, because I mean, if it's of course, important to have a good design too, but usually, as you said, I mean, you have to have few iterations before you get things right? Especially because there are some details that the simulation doesn't show, right, and all these things. So yeah. It would be great to hear from you afterwards about what was the result.
Yeah, but yeah, this I think can show to the camera.
Oh, let me just, yes.
If you guys,
Yeah, you can show the camera now.
Like this.
so,
The software screen is open, and now you have the board in your hand. So from say, consider a student that wants to do the same. How much would it cost for someone that does not have any access to anything? Start today and get something like you have in your hand.
Oh, and for this, I think my budget to this was like I made my own. I asked to money for some people, but the budget I think I go out of budget in the like in my designs because I get excited to like make the board beauty and make a good project. So I like.
There is even a picture, right?
Yeah.
That should be expensive.
And no, the picture actually don't. But the point is that the size is very big, and this goes to like a lot of.
Do you want to present to the camera? Because
yeah.
now it's getting you.
Yeah. This is the board.
Yeah.
This
You
is
can put it closer.
okay.
Yeah,
This
that's
is
good.
This is the back of the board. The drawings is not so expensive, but the area is very expensive. So
Yeah.
this is the point. But yeah, I think just for the board, not the components. the board was like this size board, and all the like the small modules that they have, they cost for fabrication on the GLC PCB 200 reais, but the full price was like 400 because 200 in taxes. We are Brazil.
Yeah.
Yeah. So, but yeah, very expensive. But for me, it was like I consider myself as like a portfolio. So, and I was like too on the project to go out but I think GLC PCB actually has like a low price things. I think could be like 100 reais, maybe 200, but I think for the board and the components it's other part.
But that's quite cheap if you're considering like you are designing some board and some product. I mean, for a starting company, for a startup, that's pretty inexpensive.
Yeah.
Consider because tooling. I'm not sure if you know the current prices, but 5 years or so, Altium Designer was really expensive. So considering that you're a student, right?
Yeah.
You could afford to design your board, and so I think that the real value here is in the tooling that you use, right?
We need to think that, of course, he's doing this by himself, but if you are a research institute, for instance, usually has tax exemptions, and it will be, less expensive, I would say. So yeah, only the license to use CAD's design tools is probably much higher than what you spend. So.
Oh no, yeah, the license part is the worst part. Yeah, I agree. The manufacturer is like consider a company is like a small price, but for me as a student it was like a lot of months of yeah.
Any other questions for Carlos? All right, thank you very much, Carlos. So now Matheus First from Instituto Eldorado is going to present about functional simulation with QEMU for rapid prototyping of risc-v matrix processing extension. Matheus?
That's a long title. Hello everybody. Thank you for attending for this presentation. Thank you, Leo and Rafael for organizing FOSForums this year again and inviting me. My name is Matheus. This is the name of the presentation. Here is some of my bio. I work at Eldorado. I work at the embedded computing department. I have a computer engineering degree and a master's in electrical engineering. And I've been working with QEMU for about 2 years, implementing mainly the Power 10 ISA and fixing random PowerPC issues. And today we'll talk about risc-v. Eldorado is starting a partnership with Barcelona Supercomputing to develop a matrix processing unit for risc-v, and I work in this project, and one of the problems that we had was to prototype the ISA. So first we'll go what functional simulation is. Usually in hardware design language, you have this idea of functional simulating. Here are two definitions from Intel and AMD. So the basic idea of functional simulating is that you are not caring about time or signal integrity. You are caring about the functional aspect, the behavior of your circuit, and not the nifty details. Here we take the idea of functional simulating because we want to simulate the ISA. We want to simulate what the instructions will do so we can test our design before we even start using the hardware description language to create the design. The idea of rapid prototyping comes from manufacturing industries. We took that to the software engineering part too. It's the idea that we will make fast prototypes. It should be cheap. You shouldn't waste too much time in your prototyping. The idea is that you will test your idea, test your business model, and then if it doesn't work, you haven't lost a lot of money. About QEMU, QEMU is a generic machine emulator and virtualizer. Today we will be mainly concerned about the emulation part. We have two types of operations with QEMU. You can emulate the complete system, like the CPU with the memory, buses, devices. That's called the system mode. And this mode can be accelerated with an hypervisor, like KVM on Linux, Hyper-V on Microsoft, and so on. There's another mode that is only for emulation, that is called user mode. With this mode, you will load an ELF binary of a foraging architecture using QEMU. QEMU will not emulate the memory or devices, just convert instructions and signals and system calls to the native architecture that you are running. And QEMU is also able to generate synthetic signals to represent events that your instructions might cause, like a SIG-U if you don't have a particular instruction implemented, or a SIG FPE if you divide by 0. Now about risc-v, I think most of you are aware what risc-v is, but the main point here is that risc-v is very small. The base ISA is 40-something instructions, and you have a lot of extensions that will add more instructions for other purposes. So here are some examples of the standard extensions that are ratified right now. You have the M extensions for integer multiply, you have the A extension for atomics, F, E, and Q for different types of floating point. So the idea is that if you are making a microcontroller, you don't need double precision float point, you can just not use the E extension. Some other extensions that are worth mentioning are the C extension for compression instructions, mainly the V extension, that is the vector one, It adds the vector registers. It was recently ratified, and it adds the vector operations. So you have 32 vector registers. They have variable lengths, and they have an implementation defined maximum length. And part of the opcode is allocated for vendor extensions, so we can make our own extensions, and we'll be sure that a standard extension will not clash with our opcodes. Right now, the vector special interest group is discussion. Whole matrix operations will be added to risc-v. You have two different groups. You have the attached matrix extension test group that is proposing that matrix operations should not depend on any other extension. So they will add two registers to hold the matrix data, and it's similar to what Intel and ARM did when they added matrix operations to their architectures. The second group is the integrated matrix extensions. They propose that we should reuse the vector registers of the V extension, and that's quite like the way that the Power architecture added matrix operations with the MMA. Okay, now I will talk. I think it should be quite obvious, but I will try to convince you all that you should use matrix extensions, you should use matrix operations. Why you should do that? The reason is the memory wall. On the recent years, the computing capacity of processors has increased faster than the bandwidth of memory. So now you have processes that, algorithms that were CPU heavy, they were CPU bound, now they are memory bound, because the memory is not fast enough to feed the processor with enough data. So to discuss this problem, I will present you the idea of computational intensity. Some authors will call that arithmetic intensity or operational intensity. It's basically the idea of how many operations you can do by unit of memory that you fetch from memory. So let's say you have a vector register of L elements. You want to multiply two registers. That will be, we will load the two registers, so it will be two L elements that will be loaded, and we will perform L multiplications. So the computational intensity would be L over 2L, that is a half. It doesn't depend on L, so even if you increase the vector length, the computational intensity will be the same, if I got the math right. And if you do the same math for a matrix operation, you have, say, a matrix that is square, is n by n. You will fetch n squared plus n squared elements. It will be 2n squared, and you will perform n at cube multiplications. So the computation intensity is n over 2. The important thing is that if you scale the n, you scale the computation intensity. So the bigger your matrix registers, the faster you should be able to compute. So with that in mind, matrix operations should be more efficient in memory. With n equals square root of L, if L is 4, we have a tie, we have a half of computational intensity. If L is 8, we have square root of 2, and L is 16, you have 2 of computational intensity. So now, why are we using QEMU? QEMU is open source for once. Most simulations for RTL designs are not open source. Some of them require additional hardware, like FPGAs, to accelerate the process. But QEMU is faster by itself. It's a simpler form of simulation. You also have user mode and system mode. User mode is quite useful to test the implementation of your instructions in compilers, to test user space libraries, and you can also test other user space applications. And then you can use the system emulation to test the kernel, to check if you are doing context switching right, if you are delivering the traps of your instructions right. or to test interaction between process and with your instructions and devices. QEMU has built-in tracing and logs that is quite useful to compare your results with other tools. QEMU has a GDB server, so you have breakpoints, watchpoints, single stepping, and there is also TCG plugins. There is a way to extend QEMU. You can use that to instrument your code and analyze your workload. So you can have just the behavior of your instruction implemented in QEMU and develop your plugins to specific analysis. That way, when you are developing your libraries, you are not paying the price of the instrumentation, but when you want to get some results from your implementation, you can turn on the plugins, and then it will take a little more time to run, but hopefully you will only run it once. Now, who will do that? So, as I told you, we don't have a matrix extension yet. It's on the works. So we came up with one of our own. This is a draft that was made by the folks at Unicamp, Lucas Avarenga, Iago Aquino, Professor Guido Araújo, Professor Lucas Wagner, and Professor Sandro Rigo. This is a very simple draft. The idea is just to test if it works, what are the problems, what are the limitations, and then iterate of that design. That's the rapid prototyping. So the first point that we want from these extensions is that we want it to look like the V, because we think that it's important to keep the ISA consistent, even between extensions. To make it simple, we made it just to the operations only on 32-bit signed integers. We made only unit-strided loads, and we make AME-like architecture, so we'll be adding 32 matrix registers. They will be of fixed size for now, 512 bits, and they will be squared matrices only. If you do the math, 32 bits, 4 rows, we'll get the 4x4 matrix. And the implementation contents will be the matrix length, that is 512 bits, and the row length, that is 128 bits. So, here's the instruction format that we decided to use. The measure of code that we use is 119, and then we use the three most significant bits to differentiate between the instructions formats. So the first format is the matrix load store instruction. It uses the minor of code 1. And then there is MRM, which is not fitting in 1 bit. So maybe we should, wait, no, maybe, you know what? Let's go with that. MRM is the masking register bit. The vector registers have this idea. You can have the vector V0 to represent a mask, so you don't operate in all the elements of the vector. We think that will be useful for matrix too. That's for future use. We will not implement that today. We also put the row stride here. We will not be implementing it right now. The idea that this RS2 field would be a general purpose register indicating how many bytes you have between rows. The RS1 would be the matrix memory address. The MOP will differentiate between the types of loads, so if it's continuous or row strided in the future. And the MD is the destination matrix register. The second type of instruction, we called it register-register movement. It's mostly for future use. We think it will be useful if we could move a particular element to a GPR, or if we could move an entire row or an entire column to a vector register. That might be very expensive in hardware, so I'm not sure if we'll proceed with that. But for now, we use this format just for one sealed instruction that we call M0. So when we use the move between GPR and a matrix register, if the GPR is X0, as is the convention, risc-v, we use the value 0. So we use that M0 instruction to just initialize the matrix. Then the actual instructions that we care about, the arithmetic. We designed 3 arithmetic instructions. The first one is the multiply add. It will multiply matrix S1 and S2. S2 is assumed to be transposed in memory, and it will accumulate the result in the destination matrix. Then we have the matrix add and the matrix subtract, and we designed a DT field to differentiate the types. As I said, today is just signed ints. In the future, we might make unsigned int and float. And as is, this ISA will not support mixed type operations. Okay, now about testing. So, we don't have a compiler that knows those instructions, so we need to come up with a way to create a program that have our instructions. We will do that with inline assembly in GCC. So, as an example, we will start with M0 instruction. OP3 fields are not used, so we fill 0, MRM is 0, and move is 1 for GPR to matrix register, and S1 is X0 to represent the 0 register. We fill everything with zeros, and the only field that we don't know yet is the destination operand. So that would be the looks of or binary value that represent the opcode of this instruction. We could do that in C with a constant and the variable that represents this operand being shift 7 bits. So this will generate the constant value that represents the instruction that the compiler would emit if the compiler had this instruction implemented. We can use some macros to make it easier to generate those instructions. So we do this stringify freq in C to stringify the constant, and then we rely on the fact that C strings will be concatenated by the preprocessor. Then the M0 instruction becomes the constant with this other value being shifted 7 bits, and then it becomes a string, and it will be glued together with .long and a new line and a tab. We can do the same for the other instructions. The matrix load will have this form, and the matrix start will have this form. That's the arithmetic instructions. And then we can finally write our test case. So we'll declare two matrices in memory. They are 4 by 4, int 32, and we will declare a third matrix that will be 0, just to be the place that will store our result. And then we use inline assembly. Inline assembly in C is quite a mysterious thing. The documentation is not great, but basically the idea is that you have a string of instructions. Again, since those are strings that the preprocessor will glue together, it will become just a single string that GCC will emit in the flow of instructions. We have to tell GCC that we are messing up with memory. So if GCC had some variable in a register, it knows that it should flush back to memory before emitting our code, and it will read back from memory after our code is emitted. The idea here is that after the first group of arguments here is the input of our of our inline assembly. We're telling the compiler that we want a register with the address of matrix 0, matrix 1, and matrix 2. In the inline assembly, they become the %0, %1, and %2 arguments. And then we use the macros to 0, the first 3 registers. We move the first argument to the register T0. We do the matrix load. We do the same for the second register, second matrix register. Then we use the multiply add, and we start the result back in the matrix M2. Okay, now we have a test case. If we run that with QEMU, we will get a illegal instruction exception because instructions are not implemented yet. Okay, now let's talk about QEMU. QEMU, specifically the TCG accelerator of QEMU, is the one that is used for emulation. It can be used in both system and user mode, and it's the only accelerator that allows cross-architecture emulation. Originally, TCG was thought as a C compiler. The front end of the C compiler that will parse the language was stripped out, and instead of that, you have a decompiler as a front end that will read the instructions from the guest, will generate the intermediate representation for that implements the guest instructions, and then you have the backend of TCG that will compile these intermediate representations to the host instructions. TCG has very simple optimizations. The idea is that it should be faster to compile a new code, so a new block of code. You will be compiling all the time that you're running a process with TCG, so it's better to generate an optimal code but do it fast than spend too much time optimizing code that will be thrown away in the future. And well, here are some examples of the TCG operations. The intermediate representations have around 190 operations. It's a RISC-like architecture that is described. So we have like branch instructions, load instructions, you have divide, bitwise char, you have rotate and shift and all those bitwise instructions. And I would like to call your attention to one special instruction, that is the call. These instructions allow the TCG code to call a C method at runtime. But we'll get back to that in a minute. So, TCG intermediate representation is quite like any other compiler. You have basic blocks that are sequence of TCG operations that are terminated by branch instructions. You have variables. You have 3 types of variables. There are temporaries that only live inside a basic block. You have local temporaries that live between basic blocks. And you have globals that will be allocated by the whole lifetime of the program. Those variables are strongly typed. They are 80, 32, or 64 bits. Recently, QEMU started to implement 128 bits variables, but that's something for the future. And you have a pointer type that is an alias to the size that can hold a pointer for the host memory. And you have the target long type that holds a word of the guest memory. Finally, you have translation blocks. The translation block is a segment of guest code made with multiple basic blocks. And here's a figure. So basically, in user mode, you have the L file that will be loaded by QEMU. The CPU loop will look at the current instruction pointer and will ask if we have a translation block for this particular address. If it does not have, it will call the translation loop. The translation loop will make will read the instructions in this address, will generate the intermediate representation, will call the host backend that will compile and generate the guest instructions. Those instructions will be written to a new page of memory. So QEMU is working like a just-in-time compiler. And then we'll go back to the CPU loop that will jump to the generated code. If something happens, like if you receive a signal, we'll go to interrupt handler. This interrupt handler will do what is necessary to unwind the stack and get a hold of what was happening to cause the interrupt. And then we go back to the start of the CPU loop. As I told you before, we have helpers. The idea is that one of TCG operations is the call. We can ask the TCG backend to emit the code necessary to call at runtime an C method. So this call will flush variables to register variables that are in register to memory. We'll prepare the ABI for the ABI call for the helper. We'll jump to the helper, and when it gets back, it will restore the state that we had before the call. By default, helpers can raise exceptions. So if something happens, QEMU will unwind the stack and try to figure out what happened. We can optimize to tell the QEMU that a particular helper does not generate exceptions. And we can also say that it doesn't have side effects. That helps with the simple optimizations that TCG does. Okay, the front end. So QEMU has this thing called the code tree. It's a Python script that is used to decode instructions. So you will define the instruction pattern in a file. We have very few minutes left. I will go a bit faster. The basic idea is that this file will define the bit pattern. So its dot is a bit that you read on the instruction. You will give name to some of those dots. And if you don't care about a particular bit, you will use the dash. And you can put the ones and zeros to represent the fixed bits. So here is the major opcode, here is the minor opcode of the instruction. And since this is the M0 that we are implementing here, that's the fixed value for the M0 operation. The documentation is in this file. If this Python script will generate C code that will make this parsing, and when it finds a match with your pattern, it will call an instruction with a fixed name. It's trans underline the name of the pattern, and it will receive a context pointer with information about the CPU and the state that the instruction was called, and a second argument with those names that you put here, like MRM, or the RS1 and RS2. In our example, it will be trans underline MMV XM. We should implement this method somewhere. Usually it's put in translate.c, but risc-v has this policy, specifically risc-v in QEMU. They include the C file from the translate.c file. It's a bit strange, but it's what the project does on most architectures. So to implement our instruction, we will add a new trans underline MPE for matrix processing engine, and that's where we will implement our translator method. So the basic idea is that the A argument will have the value of RS1. If it's not 0, then it's not the M0 seal instruction, then we will generate an illegal instruction. We are not implementing that yet. And then here we would put the logic that implements the instruction. But first, we have to add the matrix registers to the CPU. So every CPU has this structure called CPU arc state. It's later type-defed to the name of the arc, so it becomes CPU risc-v state. If we look at that, you have the vector registers allocated as an array of Win64 values. We will follow that trend. We will allocate the matrix as a linear vector, and the contents of the matrix will be laid out sequentially in a row measure order. Another point to be made is that this structure will have host engines on the 64-bit chunks. So we need to convert the engines if we are accessing something that is less than 4 bytes, 8 bytes. The vector implementation already do that. They have these macros defined to help us there. And then we add the matrix registers. Basically, we have 32 matrix registers. That's the 512-bit implementation constant. And we want it to be memory aligned for the vector, the load and store operations that that QEMU let us do and the helpers. Then we will define this method that will give us the offset of a particular matrix registers inside that vector. And we will declare a helper in helper.h that we'll call just M0. And we will call this helper from the translator loop. So, the implementation of the helper is quite simple. It will receive the pointer to the matrix. We will just set it to 0. We call that the translator loop with genHelper underscore the helper name. So, in our case, genHelper M0. And we need a pointer to, at runtime, we need to generate the pointer to the matrix. So we do that with our mreg_off method that we defined before. We'll do an addition. There is this tcgenv. That's a global variable that points to that CPU arc structure at runtime. We will add that to the offset that we have calculated here, and that will give the destination register, the pointer to the destination matrix register. And then we call genHelper M0 with that. For the arithmetic instructions, it's quite similar. The helpers will now have 3 arguments. One for the destination, one for the matrix 1, and one for the matrix 2. Here are some some macros that will help us to get the offset of a particular element inside a matrix. The previous one helped us to find out the offset of the matrix register. This one is the element inside the matrix register. I will not go over that because we are almost out of time. But the idea is that for example, our multiply accumulate helper will just go over the triple loop, that is the naive matrix multiplication. We'll get the address of the destination, ij, the first argument ik, and the second argument jk. We'll multiply and accumulate it. Pretty similar to the matrix addition and the matrix subtraction. And they are quite alike, so we can have a single translation method to help us here. We can define a prototype for the helper method, and then we can just call this method from the translate, passing the helper name. Okay, here's the load. It's very similar to. It's a 2-argument helper. We will use this method called CPU LDL data RA. CPU because we are the CPU doing the load. The instruction is executed by a CPU. We are doing a load. L is the type of the load, size. It's 32-bit. Data, it's because it's a normal load. We are using the normal memory mapping and not a special memory mapping like a device might use. And RA is because we are passing the return address. That's how QEMU will unwide the stack if we do an access violation during our computation. Same thing for store, just the CPU st method instead. Here's the definition of the helpers, and just like the arithmetics, they are basically the same code. The only thing that changes is the function, the helper function that we are calling. So we define the prototype, and we just call this do MPL DST on the trans method. I think we have time for, okay.
5 minutes.
So, can you guys see that? Those are the changes that I made to the code. Everything that I described on the slide is here, hopefully. So this is the code tree file, the patterns, and the implementation of the helpers. Now, this is already built, so it's working already. I will use this QEMU to run the tests. Here is the, oh, not this one. Here is the complete test case. So we have a method to print the matrix and one test case for each matrix. It's a quite simple test, it's not validating anything, we just visually validate the result. And then we have the QEMU binary for 64 bits. And it does a computation. You can run this computation with GDB to single step and check the steps, but basically when it goes to the instruction that we implemented, it will just do the entire computation in a single instruction, and they should give those are the right results. I hope you believe me because we are out of time. Okay, well, that's pretty much it. If we have time for some questions.
Yes, thank you very much, Matheus. Any questions to Matheus?
Quick comment. So we from this slide today, as he pointed out, we have two major work. One is integrated matrix extension, and another attached matrix extension. That's important because every new accelerator is being built on risc-v, and we need to ensure our user risc-v as basic instruction set. We need to ensure, as I started, I say, we offer the best possible matrix extensions. So this is the work that we plan to get at least freeze this year. Not this work. But this is a kind of a branch of the main work happening with risc-v International. But this part of the key work. So what you see here is a group of engineers and professors doing something locally that is really impacting globally, which means that the work Eldorado is doing with Barcelona Supercomputer Center is the first kind of concrete work towards implementing a matrix extension that's based on risc-v. This is totally new. This is built from scratch, and this is one of the most important things that we hope to ratify end of this year, beginning of next year. Why? As I said, so if you look at the major companies today, they are all using risc-v to accelerate their growth. Every single one. Google, Apple, Microsoft, NVIDIA also has risc-v as part of their GPUs. So we do need to ensure that when they use risc-v, they have the best possible performance. We're getting there, so one step at a time. But this is a concrete example of how things evolve. So there's a lot of, we discussed it as part of the definition of IME, what they're doing right now, and that's going to be a long discussion. And everything with risc-v is developed by the community, so pretty much kind of a consensus work, and that takes time. But we are in good shape today. So, and this is the bleeding edge of technology. So what they are doing here in Brazil is impacting the global, everyone around the world. So this is one of the most advanced kind of implementation of what have been discussed. So you need to ensure that this just show us that we have a lot of skills over here that can do this kind of work. So anyway, sum it up. This is a critical work for risc-v this year, and I hope that we get at least IME integrated of risc-v or at least frozen, let's say, as soon as we can. This is
I hope to.
take some time, but we get there. And yeah, this work is also recognized by the Brazilian government, so there's a huge amount of money that we hope will land Eldorado soon to help get this done. Anyway, it's part of the big plan for the Brazilian government also.
Okay, just out of curiosity, do you guys make some sort of hardware diagram of how these structures would look like?
That's the next step. So right now we are discussing what the ISA will look like in our implementation. There's a lot of things, little things to discuss. Like right now we had 2 bits for the data type. It's clear that it's not enough, but it was just our first attempt. So we have other options, like you can put the type in a CSR, but then it changes the way you do the computation. That's what we are experimenting with. So this version will never become hardware, but we will probably have a more advanced version. We will iterate over this design to try and come up with something that is feasible and useful for the hardware.
Great job.
Thank you.
Thank you, Mateus. So we have a break now. Let's say we come back at 11:10, more or less. Okay, thank you. Next, we have Julio talking about processor CI continuous integration for risc-v processors and FPGA. There might be someone joining. Victor?
Victor.
Right. The presentation will be in Portuguese this time, but yeah, welcome, Julio and Victor.
Olá.
Demorou, mas chegou, né? Não só...
Cheguei aí. Foi mal aí, galera.
Acontece. Então é isso aí, bom dia.
Bom dia.
Vou falar um pouquinho sobre verificação de processador risc-v, usando integração contínua. Falando um pouquinho sobre quem somos nós, né? Eu sou o Júlio, eu sou aluno aqui no Unicamp de Engenharia de Computação. Eu coloquei no meu hobby como IES, porque eu gosto de fazer qualquer coisa que faça barulho ou que dê pra mexer, então desde trator até FPGA, então não existe bem um hobby. Todos consigo manter. Aqui são minhas métodos de contato, meu Telegram, meu site, meu GitHub e meu e-mail, se você quiser entrar em contato, fica à vontade.
Olá, Vitor Prudente Lab, eu sou também da Engenharia da Computação. Eu não tenho Telegram, não tenho um site, mas meu GitHub está aqui, e meu e-mail também, caso contato. Questão de hobbies, eu também tenho um hobby demais para conseguir listar, então limite tendo é infinito. E é basicamente isso.
Vocês podem ver que tinha um terceiro, mas ele passou mal, então eu acho que o problema sou eu espanto as pessoas.
Eu sei do GitHub, Victor Lake.
Então, um pouquinho sobre o nosso grupo de trabalho, nosso hostiname. Nós somos alunos do LSC, que é o Laboratório de Sistemas Computacionais, ou Computer System Laboratory. A gente é aluno do professor Rodolfo, é o nosso mestre Jedi. Nós temos 5 padawans da graduação, né? Então eu, o Vitor, acho que o resto não tá aqui. O Henrico, o Gabriel e o Ângelo, que tá na TV no caso ali. Ele já estava doente quando tirou a foto.
Tá ali, o Gabriel.
Não, o outro Gabriel.
Ah, sim.
A gente tem um aluno também de mestrado, que já é o Cavaleiro Jedi, que é o Gabriel. E a gente tá aqui no IC. Se subir a escada ali, está do nosso lado. Fazendo uma breve introdução aí, como as coisas eram testadas até então. Bom, até o momento, a gente não tem bem um padrão de como testar as coisas, por vários motivos. Tem alguns trabalhos que tentaram padronizar isso, mas não conseguiram, que basicamente a gente tem vários ISOs. Então a gente tem x86, ARM e vários outros ISOs, e quase todas elas são fechadas, então a gente tem esse problema delas serem fechadas. Outro problema é que, com as coisas fechadas, geralmente as implementações também são fechadas, então tipo, geralmente a empresa ela faz a implementação, ela não testa aquela implementação, ela não divulga bem como ela testa isso. Então, sei lá, o Intel da vida, ela faz o processador, testa ele, fala que funciona e beleza, a gente não sabe quando a testa verificou ele. Então, no geral, essas coisas aí dificultam um pouco o reuso de código, o reuso de teste para estar testando processadores. E o que mudou, recentemente, né, alguns anos atrás, surgiu o risc-v, que é uma ISA aberta, um padrão aberto, e com o risc-v a gente tem um intervalo muito grande de implementações. Então, como ele é open source, qualquer um pode fazer implementação. Então, as implementações com tamanho diferente, custo diferente, investimento diferente, né, com microarquitetura diferente. Isso é muito interessante, porque pela primeira vez, acho que tem várias implementações abertas e a gente pode comparar elas e testar elas com os mesmos testes. Falando aí um pouquinho mais das implementações, como eu já falei, né, o Fab é aberto, então a gente tem um intervalo gigantesco, então desde implementações pequenininhas para sistemas embarcados, com RV32E, até processadores gigantescos, com sistema matricial, vetorial, no caso matricial não existe ainda, né, não oficialmente, para data centers e por aí vai. É só um bom exemplo, o risc-v tem um site, no site do risc-v tem uma aba de Exchange, e lá tem uma lista de cores, tem alguns cores, essa lista tem mais de 100 cores, isso que está listado lá. Só com a letra A tem por volta de 17. Inclusive um detalhe é que lá não mostra a quantidade, isso é meio triste. Porque a lista tipo, não tem fim, você vai rolando, 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 e não tem paginação e é meio triste. Mas um dia eu chego no fim. Mas minuto na vida é morango, né? Então, novas tecnologias, novos problemas. Já que eu tenho tantas implementações, surge o seguinte problema, principalmente com as open source, que é o nosso caso, beleza, como eu garanto que todo mundo segue à risca os padrões da ISA? Porque, sei lá, geralmente uma empresa maior ela faz uma implementação, ela mesma testa ela. Mas o tesouro pequenininho, um pequeno grupo de pessoas, faz a implementação, mas geralmente não tem tanta certeza se ele realmente testou ele bem, ou se ele segue à risca a ISA. E outra grande questão também que tem várias implementações, cada uma de uma arquitetura, cada um de um jeito. Então tem um cara grandão, um cara petitinho, um cara ciclo único, um cara multiciclo. Como eu uso um teste mais ou menos padrão para testar toda essa galera? Então, isso são duas perguntas que surgem aí. Então, com base nisso, a gente começou nosso trabalho, que basicamente tem o seguinte objetivo, a seguinte motivação. A gente quer fazer uma estrutura mais ou menos genérica, minimamente genérica. Então, eu quero testar várias implementações, modificando o mínimo possível a minha infraestrutura, e sem mexer muito na implementação, então eu não quero que seja invasivo, eu não quero ter que abrir o código da pessoa e modificar metade dele para poder testar. Então, isso dá muito trabalho. Eu quero que seja minimamente rápida, então eu não quero passar dias testando a implementação, eu quero conseguir testar várias delas, então tem que ser certamente tem que ser rápido.
Tem que ser fácil de reutilizar, então tem que ser bem versátil. Eu quero ter uma base grande de testes, porque o risc-v tem várias extensões, então eu quero ter um conjunto bem grande. Então, sei lá, se eu tenho uma implementação que implementa instrução I e instrução M, eu quero conseguir que você pode testar ela. Só que se eu tenho a maior, eu quero ter teste também para testar essa maior, com mais extensões. Como eu já falei, minimamente invasiva e suporta várias implementações. Só para dar aí um contexto do que isso é importante, se você pesquisar o risc-v no Google acadêmico, só o risc-v, sem nada, sem colocar mais nenhum contexto, em menos de um segundo você tem mais de 1 milhão de resultados. Então é algo que está crescendo bastante, tem muitas implementações e tem bastante trabalho aí na fase de testes ainda. Falando um pouquinho da solução, basicamente é um ambiente compartilhado de build e verificação. Então, um framework compartilhado, né? Então, a gente tem um workflow de build e teste. E uma coisa que eu citei aí, que eu vou falar mais pra frente, que a gente executa a parte dele em hardware. Isso vai ficar mais claro mais pra frente. Então, beleza. Como a gente vai fazer isso? A gente vai usar a CI, integração contínua. Falando um pouquinho mais de CI, basicamente CI está ligado a testes automatizados, mas não só isso. É quase uma metodologia. Por que eu digo isso? Porque, no geral, o CI está tipo, no fluxo todo. Então, se mais que você bem isso, eu começo no código, então a pessoa ela fez a implementação dela, no caso, um software, ela manda isso pro remote, né, para a nuvem. Então, desde que ele chegou lá, eu já começo buildando ele, eu já testo ele e já tenho um relatório de como tá. Então, tipo, é algo totalmente integrado de ponta a ponta. Então, desde o desenvolvimento até a entrega final. Esse software é algo bem consolidado já, né? Quase tudo hoje utiliza CI, mas no hardware ainda é algo bem novo. Então, geralmente, quem faz, tipo, passa para frente, a outra pessoa testa, tudo, nada, tipo, automatizado. Então, é um pouquinho trabalhoso. Então, basicamente, a ideia é, tipo, eu teria uma coisa nova, eu mandei isso pro remote, talvez os meus testes não cubram a coisa nova, mas eu garanto que o que já tinha sido implementado ainda funciona. Então, com isso, fica bem mais fácil de desenvolver. Porque se eu quebrei algo, eu já vou ter uma noção disso. Um detalhe importante é que a gente não quer só pegar os testes que a pessoa escreveu e testar eles no CI de forma automática. Então, a gente vai ter testes que a gente escreveu, a gente vai rodar os nossos testes em cima da implementação da pessoa, os testes dela e o teste dela que vai rodar na implementação de outras pessoas. Então, basicamente, é teste compartilhado. E aqui, então, beleza, como a gente vai fazer isso, né? Então, isso daqui é só uma visão de ponta a ponta. Então, do nosso fluxo, então, desde o Git cron até o build até os testes. Agora, falar um pouquinho mais de cada um. Começando aí, voltando um pouquinho passo atrás, uma coisa, um detalhe que eu falei é que eu queria rodar de forma rápida os testes. E no geral, a gente roda teste em simulação, mas simulação, principalmente nesse caso que é a implementação, então já é um processador pronto, não é uma simulação da ISA, elas são caras e lentas, porque é algo bem complexo. Então a nossa solução foi usar FPGA para isso, para estar acelerando esse fluxo. Então parte da infraestrutura ficou dentro de uma FPGA, ou de várias FPGAs. Então isso deixa um pouquinho mais rápido o nosso teste. E a FPGA tem algumas vantagens extras. Então, como vantagem, o simples fato de eu pegar a apresentação e mudar ela para a FPGA, eu tenho algumas métricas dela, como a área que ela ocupa naquela FPGA, o clock máximo dela. Outra vantagem que também tem é que a FPGA é mais próximo de um ASIC, então se você quiser um chip de implementação é algo mais próximo, a simulação é um pouco mais distante. Então, tipo, a gente fala que nem tudo que é simulável é sintetizável. Aquele carinha ali é um exemplo. Eu peguei um core aleatório do risc-v, uma lista, eu simulei ele, funcionou bonitinho, eu fui mudar para FPGA, não funcionou, fiquei magoado. Era um erro bem besta de temporização, mas... Isso aqui, essa tabela aqui é só um exemplo disso que eu comentei das métricas, né? Então aqui eu tenho 4 metações comparando, a comparação entre área em LUT, na FPGA da latency, por frequência em MHz. Então eu consigo ter esses dados, então tá, tal implementação ocupa tal área, tem tal frequência máxima, então tem alguns dados interessantes. Mas é tudo na vida é morango, né? Então a FPGA também tem alguns problemas. Primeiro que quando eu simulo um hardware, uma implementação, um hardware qualquer, eu posso basicamente parar qualquer momento da simulação e olhar, tá, o sinal tá assim, tal processador tá assim. Na FPGA isso não tem como. É uma caixinha preta, eu coloquei o hardware lá, não consigo ver o que está acontecendo. E também outro grande problema é que a FPGA, querendo ou não, a nível de infraestrutura é mais complicado. Que ao contrário da simulação que eu posso baixar um programa, abrir um shell e rodar a simulação, na FPGA eu preciso ter toolchain para buildar para ela, eu preciso ter essa FPGA fisicamente, a FPGA não é barato, preciso manter essa FPGA ligada em um PC, então tem alguns problemas, né? Nem tudo se resolve fácil. E como a gente resolveu isso? A gente fez uma casca em volta do nosso processador. Então, como assim uma casca? Eu tenho a minha FPGA, eu tenho o meu processador, e em volta dele eu tenho alguns módulos de hardware que conseguem interagir com ele. Então eu consigo controlar o clock dele, eu consigo rotear ele, resetar ele, eu consigo ler o barramento de memória, então eu consigo ver o endereço que ele está pedindo, o que ele quer escrever na memória, eu consigo fornecer os dados que ele vai ler. Então tudo que vai ler passa por esses bloquinhos, né, por esse controller. E esse controller também é capaz de falar com uma máquina externa, o que a gente chama de máquina host. Então ela consegue pegar esses dados do processador e mandar para fora, pegar os de fora e mandar para ele. Então eu consigo ter uma interação com ele mínima dentro da FPGA. Tudo isso sem invadir ele, sem modificar ele. Então, basicamente, por padrão, ele já vai ter um armamento de memória, já vai ter um clock de entrada, então eu não altero nada dele. Falando um pouquinho agora mais de software.
Perfeito. Então, para a gente fazer essa comunicação, a gente precisa de um software, um terceiro software que vai estar na máquina host, que vai fazer essa comunicação, vai fazer essa interface entre o computador e a FPGA, onde está o controller e tal. Esse é um software que vai fazer a comunicação através de UART, é uma comunicação serial, e ele basicamente vai mandar os controles e fazer... Ele pode parar o clock desse processador, ele pode mandar esse clock voltar, mandar tantos ciclos de clock especificamente, e aí tem esse protocolo que a gente vai fazer esse controle. Então, esse software também, ele vai pegar os testes que estão dentro da máquina host, e ele vai conseguir programar pegar esses programas e colocar na memória da FPGA, e a gente vai conseguir rodar esses testes, e a gente vai conseguir esses resultados de volta à máquina host. E aí, basicamente, tendo esses dados, a gente vai conseguir realizar esses testes e conseguir todos esses resultados. Mas como é que a gente está fazendo esses testes? Primeiro que a gente vai pegar os testes dos próprios processadores. Além disso, a gente também vai atrás de testes que já estão feitos. Então tem conjuntos de testes e geradores de testes aleatórios que a gente pode fazer. E a gente vai produzir os nossos próprios testes para realizar testes de determinadas funções específicas. A gente vai querer testar a DDI, a gente vai querer testar a subtração, a gente vai querer testar para gravar na memória, para fazer um jump ou algo do tipo, a gente vai fazer todos esses testes específicos. Esses dois aqui são geradores de testes aleatórios que fazem um conjunto de várias e várias instruções muito grandes, e a gente vai fazer isso baseado em comparação. Então a gente vai ter um processador ou a gente vai ter uma simulação, que a gente sabe que essa simulação está fazendo esses testes de forma correta, ele está fazendo essas instruções de forma correta, a gente faz os testes do processador, pega esse resultado na máquina host, e com esses resultados a gente faz uma comparação para ver se esse processador está fazendo esses testes de forma corretamente. E é basicamente isso. A gente faz essa comparação, se ele estiver dando certo, a gente passa para os próximos testes, se não estiver dando certo, a gente para o fluxo e a gente tem um controle de quantos testes ele conseguiu passar. A gente pega testes mais básicos e vai subindo no nível, a gente pode ver essa diferença de até onde o processador chegou a evoluir. E para isso, a gente volta para a parte do CI. O nosso objetivo não é fazer um software de CI, não é fazer esse controle do CI. Então a gente basicamente pegou o Jenkins, que é um software que já existe há muito tempo, já tem muita coisa nele, ele já está bastante desenvolvido, tem muitas extensões, add-ons, que ajudam o nosso processo, e a gente usa ele como a nossa ferramenta de integração contínua. Então basicamente ele vai ser o que a gente vai usar para controlar todo o projeto. Então dentro do Jenkins a gente pode falar, ele está na máquina host, então a gente pode fazer uma pipeline que vai mandar os comandos para cada um dos processadores, vai colocar nas FPGAs, e ele vai ter o controle de fazer isso de forma paralela, para que a gente não perca muito tempo. Ele vai ter o controle do software que vai fazer a ponte entre a FPGA, o controller e os processadores. E a gente tem algumas coisas muito boas que pode ajudar, que é um controle basicamente de quando a gente está fazendo esses testes. Então a gente tem um controle de data, horário, coisas do tipo. A gente também pode controlar ele para que esses testes sejam realizados tanto quando a gente adiciona testes novos ao sistema. Então toda vez que a gente adicionar um conjunto novo de testes, ele vai conseguir rodar em todos os processadores automaticamente, da mesma forma que se um processador mandar uma atualização, fazer um push ou algo do tipo, a gente vai conseguir fazer esses testes também automaticamente, além da gente poder fazer um set, faz teste a cada uma semana, todo dia ou algo do tipo. E a gente tem um pipeline completo e a gente tem controle desse pipeline para ver o que está acontecendo em cada fase desse pipeline. Além do histórico, obviamente. E hoje em dia, a gente, por enquanto, tem 15 processadores. Alguns deles aqui estão falhando e outros estão passando. Não necessariamente por causa do processador, é porque a gente ainda está na fase de integração de todos esses processadores. Mas nós temos vários processadores, a gente tem o controle se eles estão passando ou não. E a gente também tem os logs. E todos esses logs estão públicos, você pode entrar no nosso site e conseguir ver todos os logs de todos os processadores, ver o que está dando certo, o que está dando errado, e qual parte do teste está passando ou não está passando, quanto tempo demorou para essa execução acontecer, há quanto tempo atrás essa execução aconteceu. E aqui nós temos as FPGAs que nós temos hoje em dia sendo integradas e as que já estão em operação. A gente tem 3 que já estão sendo usadas e que a gente está fazendo os testes dos processadores dentro de cada uma dessas FPGAs. Tem 2 que ainda estão no processo de integração e a gente ainda tem o objetivo de colocar outras FPGAs.
Só pelo contexto, o que a gente fala de suportar da integrada é basicamente o seguinte: eu tenho uma FPGA X, eu consigo buildar coisa para ela, eu consigo comunicar com ela. Então, a gente tem mais algumas, só que tem sempre como usar ainda, como integrar na infraestrutura, e aí, às vezes demora um pouquinho. E aí, beleza, agora, dado tudo isso, como você pode contribuir com isso? Bom, você pode assinar um core novo na infraestrutura, então se você dá um core novo, todo log que ele gerar vai ser útil pra gente, como ele se comporta, onde ele dá certo, onde ele dá errado.
Como está tudo aberto, a gente também precisa de mais testes para o sistema, então você pode escrever testes e adicionar lá também.
Você pode mandar FPGA pra gente, que não é importante.
Você pode olhar o nosso código e ver problemas que tem nele e avisar pra gente, abrir uma issue, algo do tipo.
Você pode escrever código também, se alguém manjar de Verilog, VHDL, Assembly, a gente vai ter um pouquinho de ajuda.
E, é claro, falar sobre o projeto para outras pessoas e espalhar a palavra do CI.
Agora uma coisa importante, como adicionar um core novo, a gente não fez na página bonitinha para mandar, então você pode abrir uma issue, colocar lá o link do core na descrição, a gente responde a gente, às vezes demora um pouquinho, mas a gente responde. E algumas coisas que a gente tem em nosso horizonte ainda, tipo, tem muita coisa para fazer, mas algumas que são mais relevantes. A primeira é distribuir a infraestrutura, porque atualmente a gente tem um servidor na sala do Rodolfo e tem um monte de FPGA nele, só que chega um ponto que não cabe mais FPGA lá dentro. Então, a gente precisa distribuir isso em mais máquinas, é um desafio como distribuir isso aí ainda.
Não, é uma sala muito grande, mas
A sala é meio pequena.
por enquanto serve.
Então a gente está tentando distribuir isso, está em processo. É fazer mais testes, porque não os testes que a gente já tem pronto são testes genéricos, então às vezes alguns casos muito específicos eles não cobrem, então um caso mais de borda, então a gente tem que ver testes mais específicos. Uma coisa que a gente tem em mente aí, estou trabalhando nisso ainda, é deixar a parte de ponta da infraestrutura, então tipo, as máquinas que falam com os FPGAs e gravam são todas o risc-v. Lá no cantinho tem uma Vision 5 com FPGA gigante, FPGA maior que a Vision 5. Está em processo, a parte funciona. Inclusive, a gente teve o trabalho de colocar FPGA no OpenFPGA Loader para conseguir usar no risc-v, porque infelizmente o Vivado não suporta. Outra coisa importante é a gente quer acelerar esse fluxo, então a gente quer tirar tudo que é de UART ou SPI e trocar para PC Express quando possível e o UART para PSPI, porque o UART, pelo amor de Deus, né? Para transferência lá, a manivela. E por último, integrar mais FPGA é importante, crescer um pouquinho para conseguir testar mais coisa em paralelo. E uma coisa aí que é mais futura, mas que é uma coisa que a gente tem em mente, é fazer um seletor de processador, porque a gente tem vários dados sobre essas implementações. Então a gente tem, por exemplo, frequência máxima, área calculada em cada FPGA, quais tipos ela suporta, quais extensões ela foram testadas. Então você fazer um seletor, por exemplo, eu tenho tais cores, tal core tem tal desempenho em tal FPGA, então tem tal frequência máxima, eu ocupo tal área, então eu posso ter um seletor de cores. Então dá para fazer algo do gênero. Nossos links, se alguém quiser acessar o nosso site, o nosso GitHub, depois eu volto aqui. E acho que é isso. Agora a parte mais legal é das perguntas. Se alguém tiver pergunta aí.
Perguntas.
Das FPGAs que vocês têm, você sabe falar de marcas assim? Geralmente é qual que vocês usam?
A gente tem algumas das Zynex, a gente tem 3 das Zynex. Então tem 2 art de 100 Rock Logic e uma grandona, aquelas Vertex. A gente tem uma da Leitz, uma Colorlight, e tem uma Tang Nano. A gente está tentando integrar uma Altera, uma Synchrony 10, só que a Altera...
E como que vocês estão fazendo para criar o core, para compilar o Verilog em algo para FPGA? Vocês usam ferramentas open source ou vocês têm que colocar ferramentas proprietárias no pipeline?
A gente usa os dois. A gente usa tanto a open source quanto a proprietária. Deixa eu voltar lá. Esse carinha aqui eu acho que tem mais coisa. Então a gente tem tanto a proprietária, né, no caso daqui do Go e privado, mas também suporta o fluxo open source. A gente até tenta comparar ambos para ver, tipo, questão de eficiência. Tipo, a área que cada um vai ocupar.
Você sabe dizer se a open source ela vai funcionar para todos os fabricantes ou é muito limitado?
É bem limitado.
É bem limitado.
Basicamente, a que funciona melhor são as da Leitz, que tem um desempenho muito próximo da oferta do fabricante. A Leitz abriu bastante coisa, mas, por exemplo, para a Goinha a open source suporta, mas, por exemplo, o uso de memória é horrível. Ela não sabe usar memória. Para as Zynex ainda está engatinhando. E para a Altera, o pessoal acho que nem tentou.
Obrigado.
Eu lembro também, pelo menos quando estava na IBM ainda, o pessoal falava que Verilog tem um bom suporte, mas você vai para VHDL, por exemplo, parece que
Isso é verdade.
é bem mais complicado. Eu lembro que para portar o Microwatt, por exemplo, lá do PowerPC, para VHDL foi um parto, porque o suporte das ferramentas open source, no caso, era bem limitado.
Inclusive no Talate, por exemplo, o iOS, que é o sintetizador, só suporta Verilog.
Só Verilog, né?
Para usar VHDL sem que usar um plugin.
É verdade. É o plugin de HDL.
Algumas perguntas, né?
Tá?
Acho que esse é o ponto. A primeira coisa que eu queria perguntar, vocês fizeram uma caça para o processador.
Uhum.
O quanto de, tipo, quão significativo em comparação, por exemplo, aos cores menores como o da risc-v, se não me engano? O quão grande é esse
Tipo, ela é quase irrelevante, porque tipo, a parte da memória o Core já ia ter, então a gente compartilha a memória. E a parte da lógica em si é como se fosse uma máquina de estado e uma serial. Então tipo, é quase irrelevante. É quase 1 para 10 num core minúsculo. Um core maior, tipo, é quase imperceptível.
E é só leituras ou também pode, sei lá, forçar algum estado?
Pode até se você fala dos dados do processador ou...
É isso, tipo, é só saída, você só ler, ou também você pode, tipo, sei lá, digamos que, não, eu quero interromper o clock, a máquina instala e forçar, pular o instalo, porque é que você quer.
No caso do processador é só leitura, só consigo os dados que ele retorna. O máximo que eu consigo fazer com ele, sei lá, é parar o clock dele e resetar ele, por exemplo. Ou só poder controlar o que ele valia do barramento.
a respeito da infraestrutura que vocês estão montando, de software e tudo mais. Tipo, vocês contaram que eu servidor com vocês, mas, por exemplo, eu na minha casa quero desenvolver risc-v, tenho uma Raspberry. Tipo, eu poderia tipo, integrar com uma, por exemplo, da Linano e tudo funcionaria? Tipo, é muito pesado para isso ou não?
Por tese tudo funcionaria, a única coisa que vai limitar é a questão das toolchain para buildar. O que mais pesado nessa história aí é as ferramentas de build. O famoso quartos com 200 GB.
Mas com iOS, então...
Com iOS funciona.
E outra pergunta, de análise de testes falando que era aleatório, vocês pensaram em usar alguma metodologia de, tipo, para parte de teste, alguma verificação funcional, alguma coisa de teste caixa branca, alguma metodologia de, tipo, verificar a corretude da arquitetura, vocês usaram alguma coisa formal?
Essa parte formal a gente não chegou a tratar tanto. A gente está mais na parte aleatória e parte de coexecução. Então, tipo, a gente tem um modelo de ouro, todas as implementações e comparar elas.
Uma das coisas que... Uma coisa é você pegar uma implementação do chip, ou do processador, e rodar para ver se tudo ok. Mas tem uma outra parte disso, que é você garantir que aquele processador, ou aquela implementação, é coerente com o que está definido na ISO.
Sim.
Vocês pretendem fazer isso? É um ponto de validação importante, porque... Beleza, funciona. Tá. Mas é compliant com a ISO? Fala, eu posso chamar esse processador, essa implementação de uma implementação risc-v compatível com risc-v? Porque isso é mais importante ainda para quem vai consumir. Ou seja lá o que for. Então, vocês pretendem fazer isso?
A gente não chegou a pensar nisso ainda.
O Rodolfo já pensou.
Rodolfo provavelmente. O Rodolfo já pensou, mas não contou pra gente. Acontece.
Na verdade, vocês não ouvem isso. Mas beleza. Comparando, tem uma necessidade de certificação desse cenário, em que as implementações são verificadas para garantir que elas implementam aquilo que está descrito na ISO. Então, vão existir laboratórios ao redor do mundo todo, vai ter um no Brasil, para fazer esse tipo de coisa. Então,
provavelmente o Rodolfo já está vendo isso, mas
desse trabalho vai ser aproveitado.
até chegar aqui demorou um pouquinho.
Uma curiosidade sobre como funciona o teste, não faço uma ideia. Vocês conseguem enviar esse código para ser rodado lá, ou a rotina de validação de teste ela vai embutida dentro do Verilog, do HDL? Como é que se vocês conseguem trocar esses scripts ali em tempo de execução, como é que funciona?
Um pouco de cada. Eu consigo carregar um curso de teste inicial junto com a implementação, mas eu consigo trocar ele ao longo da execução. Então, tipo, o controle ele é capaz de, sei lá, para o croc, ele recebe via serial, no caso, por exemplo, o teste 9 e altera na memória, por exemplo. Ele consegue fazer isso.
E os resultados vocês pegam lendo a memória usando alguma ferramenta da placa?
Sim, sim. Eita.
Pô, parabéns, pessoal, muito bom. Muito legal o que vocês estão fazendo, parabéns mesmo. Vocês já publicaram artigos? Daí vocês não publicaram, vocês deveriam, falando em termos acadêmicos.
E que tipo de risc-v vocês estão sintetizando e testando?
Tá.
Se é 32, 64 bits?
Da primeira pergunta, a gente escreveu um artigo, a gente chegou a mandar ele, mas saiu dia 9 o resultado. Tá quase. Algumas semaninhas tristes. E até agora eu fiz tudo, todos os cores que a gente tem, são todos de 32 bits, são todos menorzinhos. Todo mundo tá lá em 32 bits. A gente focou primeiro nos menorzinhos, que são a maioria dos abertos são menores, então eu foco primeiro para as pessoas menores.
Como portável, assim, tipo, supondo, por exemplo, eu gosto, assim, a parte de CIs com o FPGA realmente está em falta. E assim, por exemplo, vamos dizer que eu quero fazer um projeto pessoal, quero fazer uma arquitetura antiga, por exemplo. Então, como portável é o código de vocês se eu consigo, por exemplo, ao invés de testar risc-v, testar outro tipo de projeto meu, tipo, mas tem a mesma coisa, a mesma flexibilidade de análise que vocês estão fazendo? Tipo, como portável é o código?
Bom, em tese seria só trocar os testes. Em vez de teste para risc-v, tipo, toda a parte de teste trocar para outra arquitetura. Porque a parte de hardware, querendo ou não, é muito parecida. Porque, querendo ou não, em teste vai ter um armamento de memória, vai ter ainda essa entrada de sinal, então a parte de hardware aproveita tudo. Só a gente trocar os testes.
Mais alguma pergunta? Obrigado, Júlio, Vitor. So next up is Rafael from Center for Advanced Research, Werner von Braun. He will talk about From Brazil to the World, BIPs and Chip Inventor. Yes. Thank you very much, Rafael.
Thank you, Leo. Thank you, Rafael, also. It's an honor and a pleasure to be here with you guys. Thank you for the opportunity of being here with you.
Just a moment before you start. I believe they do not know, but everything that happened with risc-v in the last 1 year started with that guy. But that guy introduced me to the government, and then we started talking. So that he was the starting point for everything we are doing with it.
Thank you, but you asked. You said, I can't reach the government, they don't talk to me. You tried. And thank you, it's a pleasure to be helping this ecosystem. Guys, I will talk quickly about two subjects, okay? First, about BIPs. It's an open source tool. I had the pleasure to start this project in 2020 or 2019, I don't remember. And about Chip Inventor, that is a startup company that we created from Von Braun Labs, okay? So that's why I'm dressed like a businessman, because now I am a startup co-founder, okay? So let's talk a little bit about BIPs. Okay, everyone knows about embedded systems here, so I'll just jump here. But I wanted to talk that there are a lot of new tools that are making it easier to play and to work with hardware. MicroPython, CircuitPython, I don't know if you ever heard about such Python versions for small microcontrollers. And I didn't like these tools very much. I was a good critic of such tools. But as I started testing, It's too much slow than C. I compared, like 100 times is lower. But for users to get started and prototype fast projects, it's very nice. And the hardware is very cheap and affordable. So everyone here, I think, knows the ESP8266, ESP32, whatever. And there is even Snack. I don't know if you guys know Snack. I didn't believe until I used it. It's a Python interpreter for Arduino. And you get a REPL, a shell. On Arduino, you can type Python commands and run Python programs, small Python programs. It was created recently by a guy called Packard. And he works for Hewlett Packard, but there's no relation, okay? But these hardware are very cheap. I am crazy trying to get a Raspberry Pi Pico 2, which uses a risc-v core. I even asked Rafael, and he said the whole world is asking for it. You're not the only one. But I don't know if you guys know, there is the ESP32C3. It's risc-v based, and it's amazingly cheap. I bought, it's like R$5 or $1, and you can get that on AliExpress or even Mercado Livre. And there is a version with a display, if you want to take a look, it's like $10, full color, high resolution display. This one, I think you guys also know, it's like R$9, less than $1 also. I don't know if you guys know, all these boards run MicroPython. There is the C6 also, which runs also MicroPython. It's risc-v, the microcontroller that is inside this board. And I started playing around and using this to teach young students at schools, and they had a lot of trouble to install the tools. Install the tools, configure the tools, set up the hardware, whatever. So I thought, why not create a platform, a web-based platform, to help people get started in such tools? That's Bipes, and I hope to explain it soon. And it got a lot of attention because as Raspberry Pi Pico was released, I don't remember when, like 2021, I just had released Bipes, and I added an option for a Raspberry Pi Pico in Bipes, and a lot of guys started using worldwide. It was very nice. And what's the idea of Bipes? It's a block-based platform based on Google Blockly. You can create programs, from simple programs to complex programs. We have AI blocks, we have Internet of Things blocks, MQTT, web server, we have email, a lot of blocks ready to use that will automatically generate Python code. From this Python code that is automatically generated, we have used the Web Serial API. I don't know if you guys ever heard about, but as we started Bipes project, W3C created this standard, and you can connect and control web USB devices from the web browser directly, USB and Bluetooth devices. So we can load this code to a low-cost board directly from the web browser. You don't have to install anything, configure anything, plug in, nothing. You just open the web browser and it starts working. More than that, Bipes is a PWA, a progressive web app. So you can open your smartphone, Chromebook, any web browser. I tested it even on console, on video games or smart TVs, and you can install it. You can disconnect from the internet and use it offline. So it's open source GPL, it's on GitHub, based on Google Blockly. It's full HTML and JavaScript, so you just have a basic web browser. You can load code on the boards using USB, serial ports, Bluetooth or Wi-Fi. Absolutely no install, no plugins needed. We have a file manager. If you prefer to use direct Python, you have a tab in Bipes that you can type your program, your Python program. And we have a file manager on the board. So you can have several scripts on the board and select which one you want to edit, run, etc. We have in MQTT, we have an IoT dashboard that you can drag and drop blocks and create an IoT application in 5 minutes. I can show it later if anyone is interested. You can share code by just sending a link. Multiple boards and blocks from small boards. We are supporting even Arduino using the snack-lang. Until x86 and risc-v full-blown devices with Linux operating system that we can load even OpenCV applications created by blocks. Okay, these are some of the supported boards. We have created some ebooks about BIPes and about nanosatellites programming using BIPes. This is a nanosatellite based on an ESP32. It's a prototype, but actually you can launch this into space, and you can program it by blocks using BIPes, okay? It's true. Carlos Craveiro can confirm that, I think. Some numbers about BIPes project. Right now we have about 30,000 users worldwide. It's completely free. You just access bipes.net.br, and I was very. We need to have BR in the address, okay? It's from Brazil to the world. More than 100 people from more than 100 countries using BIPes. More than 100,000 sessions of IoT devices sending data that you can visualize, collect data, see it in real time, and see historic data. We had 10,000 downloads from the ebooks. Many users in China. We have a Chinese version, other languages. Many users in USA, Germany, a lot of users, Australia, Canada. These are the main countries using BIPes. And for some times, Brazil was the 3rd, 4th, 5th country using BIPes. Several academic papers and final course papers, whatever, based on BIPes. And some companies are now using BIPes as their programming platform for their products. So I don't know if you guys know Robocore. It's a famous company here in Brazil that does hardware for robotics and hobby. And they have a Robocore IDE. So if you search Google Robocore IDE, you will see BIPes there and powered by BIPes. They customize it. This is one of their boards that you can program using BIPes. And we were very happy because we are in Brazil and it's a Brazilian company. Pion, Pet, Magic Big, this is an Indian company using BIPes on an educational product, whatever. We have a GitHub if anyone wants to contribute. It's GitHub/BIPes. We got some stars. I am very happy with that. Someone is liking the project, I think. This guy, Jim Tenenbaum, is helping us a lot. I actually don't have time to work on the project I am not having time over the last 2 years, but this guy started contributing and started writing documents, whatever, and he's helping a lot with the Raspberry Pi stuff. Guys, this is a complete, full example of an ESP32 board with a temperature and a humidity sensor. This is a dev board from Embarcados. I don't know if you know Fábio Souza. This is a board he created. And start the sensor, start an MQTT session, measure, print the text to the console. We have a serial console from the web browser. You can connect anything serial and interact with it. Publish to MQTT, delay 1 second, and that's it. You click play from the web browser, you load the board, and it's running here. And it's stored on the board. You can disconnect from the PC, connect to a power source, a battery, and it will be running. We can try this example later if you want. And you can see a dashboard in real time. You can plot graphs, whatever. It's good for prototyping, okay? Quick prototyping IoT stuff. little automations, whatever. Well, it's Python. It will not have a great performance, but you can quickly get some stuff done. We are working with kids using BIPes, and it's working very well. We've done many classes with kids, and they easily get it. Of course, there is a Portuguese version, and you can. Let me see if I can show it quickly.
I don't have a browser there.
Okay, no problem. I can show it later. Okay, this is the first subject. Now we pass to the second.
So, can I ask a question?
Yes, please.
What was the purpose initially to create BIPes? Because I mean, I was just thinking while we were talking that, you know, my kids, when they were younger, they went to some robotics class, and there is, I think, an MIT website, I forgot the name, but anyway, that has this block things that you can build programs and then, you know, control some boards and some controllers. So it's really perfect for education. But was that the initial purpose, or I mean, why did you create that?
This was the main goal, Leo, because we were doing workshops at schools, hands-on workshops at schools, and each school we went, you don't have permission to install software. You don't have permission to access the serial port. The technician is not here now to help. The kids don't have a computer because BIPes works on a tablet, on a Chromebook, or on a smartphone. So the main idea was to make it easier to get started and do something quick in a fast workshop, like 2 hours.
No, that's great. I mean, I know Von Braun also takes advantage of Legge Informatica, I suppose.
Yes.
Right? And one of the biggest things that it sponsors in Brazil is educational programs, right? So it's really great to see that, you know, something like this from here. Yeah.
Oh, thank you. And it's GPL, okay, guys, open source tool. And it's open for anyone that wants to use or contribute. It will be very nice to have more guys from Brazil contributing. So the second topic that I wanted to talk, this is a startup company we created, okay? I work for Von Braun Labs, like Eldorado, it's a research center here in Campinas, and we created this startup company that is a web-based platform to design chips, okay? It's an EDA tool based on the web that integrates about 40 open source tools in a seamless way to create, test, and fabricate an ASIC. Okay, so let's talk a little bit about that. I don't know if everyone here knows Von Braun. It's a non-profit research center here in Campinas. We are very well known for the Sem Parar chip. Okay, that chip you use for tolling was developed, designed, and created in Von Braun Labs, and it's 1 millimeter square. I think it's amazing. It was created here in Campinas. This is very nice. It's considered the fastest chip in the world. Still today, there's more than 10 years that this chip was created, and it has AES, cryptography, and a lot of advanced stuff, and it has no battery, and a lot of other interesting stuff, okay? Guys, so we have a microelectronics team that is used to commercial standard tools for chip development. But these tools, I don't know if you guys are used to, are expensive, hard to use, hard to access, you have to sign NDAs, it's very complicated to use such tools. And they are not integrated with prototyping in an FPGA board or with fabrication. You have to talk to a foundry, get a PDK. You have to test on another platform to test on the FPGA. So we thought, why don't we create a platform that you can drag and drop blocks to create a design. Each block has a Verilog code, and it will generate the top module automatically. We have an AI assistant. You can ask, I want a block that does an AES 128 engine. The block will pop on the screen with the Verilog code. You can synthesize, load an FPGA board and test from the web browser. You like that you can do test benches, professional test benches online, and if you also want to fabricate, you can order a silicon tape out directly from the tool. This is the idea of the tool. This is the value proposition of the business, okay, guys? But it integrates a lot of open source tools that we hope to contribute also. So I talked a little bit about this, and I was talking to Rafael just when we arrived. Europe is very interested. He was telling me, not me telling me. Europe is very interested in open source tools for semiconductors because it is strategic. Now this is strategic for every country. And DARPA, the US government, is putting a lot of money for open source tools for chip design, like more than $1 billion was already spent. For example, in Open Road project, it's an open source tool for digital chip synthesis. Okay, there's also OpenLane, some open PGKs. PGKs are the libraries from the chip fabrication plants, from the chip fabs, which are usually confidential. You have to sign confidential agreements to access each PDK, process design kit, which has the recipe, the rules to fabricate in each factory, okay? But open source tools are growing too much, and this for me is a great success case. It's very recent. Some guys from Europe designed a full open source risc-v processor. It's called Basilisk. They synthesize it entirely on open source tools and fabricate it, capable of running Linux. Okay, thank you. So, many people were saying, open source tools are not too good to create good hardware. But now you have a full processor running full Linux, risc-v, 64 bits, actually fabricated and running a full version of Linux with MMU, everything else. So open source tools, in my humble opinion, okay, are powerful, yes, but they are very hard to understand, very hard to use, and there are a lot of things that you must know a lot about the ecosystem and a lot about a lot of tools to integrate them and use them. So our idea was to integrate all that onto a web-based platform, so you can design, simulate and test, run test benches, synthesize and fabricate. This is the AI block creator, I said, and I don't know if... there's no browser here to show a video.
Well, you can try.
I wanted to let me try to show a video. I can show you open link. Okay,
okay,
seems that
it's working, yeah. Good.
Guys, this is a quick example of Chip Inventor. You go to chipinventor.com, you can create an account, it's open right now. We are creating a calculator using this AI assistant. You ask for the calculator block. And what is interesting is that you can do the project with the FPGA and port to Silicon. So the main idea is one project, one high-level project, several outputs that can be FPGA, simulator, test bench, or real Silicon. We have added support to several FPGA boards. Okay, now our main FPGA is from GoWin, Tangnano 9K. We have created this dev board. It's for education, okay, with Tangnano 9K, but it's low cost. It's like $50. I'll pass if anyone wants to take a look. Have you seen that the block automatically, the user automatically created the Verilog code for the calculator? It is seen as a block. You can connect input and outputs. As I said, we integrated more than 40 open source tools, okay, here, and some proprietary tools that we created internally. You will see digital.js inside here. You might know digital.js, some guys here. That's great. So we automatically created this calculator block. We are putting inputs here. We will put an output and simulate this device. Then we can load the FPGA and maybe fabricate. Okay, guys. We are also supporting Lattice FPGAs. If anyone wants to take a look, this is a Lattice FPGA that we are supporting. And this is something that I am really proud of. This is a small loader that we created. It runs Linux and it costs like $10. And we run OpenFPGA loader here. So you don't have to have the toolchain installed on your PC. You connect this to the USB port from the web browser. You load the bit string and load the FPGA using this Linux. Have you seen working the calculator? What's more? We are enthusiastic about this new FPGA from Gowin. It's you can buy the Tang Nano 138K. Have you heard about 138K, 1000 lutz, and it's cheap. You have gigahertz, a lot of gigahertz interfaces, 2 gigabytes of RAM. 512 mega of flash, and there are a lot of LUTs here. So we are playing with a lot of cores here, and maybe HPC can be tested here because there are a lot of gates here. And we added some compatibility on Chip Inventor for that too. It's cheap, okay? It's like 700 reais. The dev board with display, whatever. A Xilinx like that would cost $10,000 easily. Have you seen it working as I spoke? Okay, you did the project on Chip Inventor. No, I am jumping here. Okay, guys, sorry. This is an example of a DC motor control system, a closed loop control system that you can add inputs, outputs. You can, this is not, this is a ultrasound sensor for distance measurement. I will show the closed loop control later. But you have we created 300 blocks ready to use. So you have SPI, I2C, all of them are Verilog blocks that you can connect. You don't need to use blocks if you don't want. If you want, you can go directly to code. We have a code editor online. And this is the... Let me see if I can show. This is a closed loop control system that you can create in like 10 minutes. You have the input. You know DC motor quadrature encoders to measure angle. We have a DC motor with an angle sensor. It's a optical quadrature encoder. You can create a block quadrature encoder, connect to a comparator, a set point, and an output to a power driver, and the motor position will be kept at the same. If you try to spin, the wheel will always get back to the desired position. This was created like in 10-20 minutes, okay guys? Just connecting blocks. And then you can load the FPGA and test. Thank you. Guys, we have also created a risc-v in a block-based approach. This is a Pico RV32, okay? It's a small microcontroller. We tested on the FPGA Tang Nano 9K. We validated it. Okay, it's good. We sent for tape out using a Chip Ignite program from eFabulous. Now We are doing a close cooperation with the guys from Wefabulous. I don't know if you guys know Wefabulous. It's a great company. They are promoting open source hardware design, open source tools, and affordable fabrication to semiconductor. We done in the past, and it costs like thousands of dollars to do one test. Really thousands, hundreds of thousands of dollars. And now for $10,000, you can fabricate your chip. And right now they created another product. It's mini Caravelle that for $3,000 you can fabricate your own chip in silicon in small quantities. It's amazingly cheap, okay, for semiconductors. So we designed, tested on the FPGA, and sent for fabrication. Okay, now it takes like 5 to 6 months to fabricate. We have this text editor, simulator, test benches, waveform visualization on the web, the dev board I showed, the FPGA loader I also showed, and we have added compatibility to several foundries. You can select the FPGA or the fab plant. Okay, you can fabricate with Skywater 130, IHP in Germany 130, and we had a good talk with Global Foundries. We started with 180, which is an open source PDK, but we just got access to 55 nanometers PDK to add to Chip Inventor. Okay, this is one client of us that designed one processor using Chip Inventor. Okay. Thank you, Rafael, for posting that. We said, we got something here. Okay, I will post that, so thank you. And we are proud to be also strategic members, as our startup is a strategic member of risc-v. Here it is my contact. And one last stuff that is interesting, Tiny Tapeout. Just a message that might be interesting for you guys. Tiny Tapeout is another affordable way to get access to hardware fabrication. This is a Tiny Tapeout we have done from Chip Inventor. You can do in Chip Inventor and fabricate with Tiny Tapeout. It's like $300 and you get your own silicon fabricated with a dev board. And it's very nice. The guy, Matt Van, that created this, you have 500 slots here. And he puts 500 designs into the same chip with a multiplexer. And there are some jumper boards, some jumper here that you select the design you want to access. Everyone gets all the designs from everyone. And then you select, I want the design 1, 2, 3, 4, 5. So it must be open source, okay, to be sent to Tiny Tapeout, but it's very affordable and very nice to have real silicon of your device. So we have a piano chip here that we did with some kids. We went to a school, created a little piano to 5 basic musical tones. We tested on the FPGA with the kids, 9, 10, 11 years old, and we said, now we will fabricate this piano chip you created. Then we ordered a Tiny Tapeout and it's here. We can talk about it later. Okay, that's it, guys. I was fast also. Thank you for your time.
Thank you, Rafael. Any questions?
I have 2 questions. One is how we connect. For instance, I do design using Chip Inventor. And now I want to check how that works, connecting to their CI. Can I do that?
It would be lovely to do that. Let's talk. It would be great.
Second question. I did my chip design. Now I need to ensure it is compliant with risc-v. Is adding the compliance layer in your roadmap for Chip Inventor, let's say as part of the end process, before sending that to the foundry, you do a click the button, run the kind of test to ensure it is compliant, the compliance test, and then you move forward.
For sure, we have done that with Wefabulous. Wefabulous asked us for a pre-check before submitting the fabrication files, we call GDS files for fabrication. They ask for a validation, so we have added a pre-check step to validate the designs before sending to them. But we have user scripts, so we could add a user script that runs some synthesis tools and some validation tool. It would be nice. We can talk about that.
Okay. First of all, what an amazing project. Congratulations.
Thank you.
I would like to ask if you have plans about adding support for analog designs, for example, maybe some netlist extraction and all the good stuff.
Thank you, Ivan. Actually, we have an investor that has offered support for us to develop an analog version of Chip Inventor. It's ongoing, and there is a schematic capture and design connected to the Foundry PGKs. We have a prototype already, and we plan to have a product by December in 3 or 4 months. You extract the netlist, you have the SPICE simulation online, and we have the analog editor of the chip, of the analog layout. So it's an ongoing work right now. Thank you for asking. That's good to say. We think this is novel. We saw nothing similar until today, and we hope to contribute with that.
Practice is quite a workflow to say the least. Like, you need to get the schematic, you then generate the layout, do the routing, specify where everything is. Oh my god, this difference and flyer needs to be symmetric, otherwise not will work, because yes. So I imagine it will be quite a lot of work for you guys ahead. But I hope everything works fine for you.
My question.
Me too, thanks.
My question was about the current state of the analog design, but everyone already made the question. The question that I have is, for example, for me, one of the major barriers to open source tools to design hardware is the documentation. So very hard documentation. I like to ask, is the Chip Inventor investing in taking these open source tools and make tutorials, videos, documentation? How is it?
We have some guys working on tutorials, video tutorials, and some, how can I say, some didactic checklists, roteiros didáticos, I don't know.
Checklists.
Checklists to step-by-step instructions to create some designs. And we plan to have that available, especially for education, for some education situations and some specific professional case. We plan to have that.
Go ahead. Just speak loudly.
Okay. Well, I guess first of all, I would like to congratulate you guys again for this project. It's truly amazing. I've never seen something like this before. But I have a bunch of questions, but I guess I could ask some of them later if you want. I'd love to talk to you. But what I'm mostly curious about is, well, everybody that has dealt with hardware design or even just some more simple stuff like flashing dev boards knows that the toolchain usually is very, very, it takes a lot of processing power, right? Especially for FPGA design. I've already used the battle before, or it's very familiar with how long it takes to compile their designs. And you mentioned all of this is run in the browser, right? I'm just wondering if this is actually done locally, or if you guys kind of offload this board for to a central server or something like that.
That's a great question. Thank you for asking, because this is good to talk about. We have something that we have some parts of the tool that's WebAssembly, like simulation, but the synthesis runs on the cloud. And as we started creating the tool, we saw some designs that took 1, 2, 3 hours to synthesize, and we have a QE, and everyone had to wait on that QE, and this was not good. So what we have recently added to the platform is each user gets a dedicated instance on the cloud. So if you start a synthesis yourself, you will get your own virtual machine. You won't have to do it explicitly, but you will have your own virtual machine on the cloud, your instance, running all your synthesis tools, and you can control what is happening there. If you are an expert user, but if you are not, you just click and see the logs and interact with high-level options. So synthesis is on the cloud, using OpenLane, OpenRoads, Magic, Icarus, Ivory Log, and a lot of other stuff that we are talking about today. Next, PNR, I don't remember, EOSIS, whatever, and other tools.
And just like a small follow-up to that, I've done a little bit. You mentioned like for Bipus, right? The other project for like block, I guess coding for microcontrollers. I've done a little bit of robotics like here in college, and one of the main pain points we had was that even on like well-known, like well-established platforms, I guess, like for example Zephyr, the RTOS or EmbeddOS, the like actually flashing the firmware onto the board was very it was always problematic, right? Like, did you guys take any kind of special approach to make this process smoother, especially for like the other projects you mentioned where kids are like working with microcontrollers? Did you do anything special?
Yes, perfect. And just a parenthesis, I have a dream. We create a risc-v, load a risc-v that runs a MicroPython and can program with BIPes. Okay, but answering your question. In the last version of Chip Inventor, we had a C code section that you could edit C code, you could compile and load the C code into the risc-v processor running as a soft core on the FPGA board. We had that all from the web browser, and we are doing a lot of changes, and this is not available right now, but the idea is to get this back. Because I agree with you, it's hard to load the firmware, test, whatever. And we have also, I didn't bring today, but we have done a full tape out with eFabulous and Caravel, the harness chip that eFabulous uses. It brings a risc-v microcontroller embedded. If you want that, or if you don't want, you get a risc-v as a gift on your chip from eFabulous, and we have done some stuff to try to load automatically code into this processor, also from the web browser using USB port. I don't know if I answered. Okay. I think I have a video how it worked, but it will get back. It's not working right now. It's not available, but we plan to get it back. Okay. Thank you for the question.
In fact, my question is very like the one he asked. Bipes, you say it runs from the browser. Should I suppose that like the compiler or anything that it will run for the cloud, or it will run directly from the browser in this case?
Bipes is fully HTML and JavaScript.
Amazing.
You can get the HTML files into a folder, click index.html and get it working.
Oh, amazing.
From a thumb drive.
Amazing.
But I would have a follow-up question, but please go on.
Okay, so first of all, I would like to congratulate on this amazing project, both of them. And
thank you.
I was particularly curious about the AI assistant that you showed that runs on Bytes, because I was curious, like you said that you are using a lot of open source tools, And I would like to ask if it is the model that you're using is open source or is calling an API, and if it is an open source model, it is running on the browser on the machine of the user, or is running on the cloud system? It is kind of related.
Okay, right now, Bipes does not have AI assistant, it's in Chip Inventor. I want to add in Bipes, it's possible, just didn't have time to do that. But we have that in Chip Inventor, that's the calculator example we showed. And we have trained specialist system in 2 existing LLMs. And we have tested ChatGPT and we have tested the Google Gemini. And if you enter Chip Inventor, you can select which one you want to use. And for Verilog generation, with the training we did, Google Gemini is much better, in our opinion. It generates good Verilog code. We were working a little bit, and we plan to work a little bit more with Llama, Body, whoever, which are locally trained, your own LLM, okay, or a small LM. That's in our plans also, but we are getting something as we want right now. It was a good place to start.
Okay. And you guys, what kind of fine-tuning are you doing on the model to generate?
You can train. You have APIs to train, and we have added some Verilog code that we had from our IPs, and some from books, and we did some training, and that's the output you have.
Thank you.
Thank you.
A follow-up question would be regarding Bipes. Well, first, it's amazing how it will make it easier for people to really implement stuff like beginners and people for hobbyists. I think it's amazing how you can buy some cheap piece of hardware and program and actually do stuff with that. So it's amazing. I think it's amazing. But I have a question. I mean, it just works with Python as of today, right?
Yes.
Any chance, any idea that it will also in the future work with other programming languages? You are planning to implement that?
Yes. We had an idea of generating C code, compiling C code and loading C code. And we have done some work. And we have managed to load C code in bare metal from the web browser. This is already working into Arduino and into ESP boards. And it wouldn't be very hard to compile a C code on the cloud. And to generate, there are some generators ready. So it's an integration work that should be done. And it's about time. I think it would be C code generation would be very nice, in my opinion.
That would require to run, like, to compile in the cloud then. So there is no plan of like trying to compile some subset of C directly on the web browser.
Wow, that's a great idea. Maybe with WebAssembly, but it would be a lot of work, I think.
Yeah, I suppose so. Yeah.
But this would be very nice. Let me see if I can show. I just connected a board here. Serial. This is interesting. Web serial API is not enabled. So we need.
I said.
So it's blocked here anyway.
It's my computer.
It's your computer.
Yes. That's why.
Okay. But guys, here we have blocks. There are a lot of blocks, okay? Sensors, communication, we have Modbus communication, GSM, I2C. You can add a GSM board, you can use a GPS. You have a serial console, a file manager, you can share projects, you have the device option, and there are a lot of devices. ESP32, Beagle board, there is even Lego compatibility, okay? Robocore board. Here it is the IoT that you can create dashboards quickly. you drag and drop, and you can share this dashboard. It's responsive, and you can open your smartphone. That's it. Okay. I think I talked too much.
Very nice. Any other questions? Well, anyway, we will have lunchtime now, and you can ask more questions during lunch if you want. Thank you very much, Rafael.
Thank you, guys.
So we'll be back at 2, and I will lock the doors. So if you want to leave stuff here, feel free. Okay? Thank you very much. Teste. Teste. Welcome back, folks. We're going to restart again. This afternoon, it will be more focused on software. The software side, we will start with GNU Enterprise Linux development and kernel debugging with Desnes, our guy from the north of Brazil.
Yes.
So, the floor is yours.
Awesome. Well, first of all, thank you very much, Leo, Rafael. Today, I want to at least try to find new folks to work with me in the future, hopefully. So basically, what I'm finding is more and more everything is just more abstract. So basically, there is AI, there is all this bunch of APIs and all this stuff that. In all of these new tools and all of these new brand stuff, everything runs somewhere. And for more and more, I'm seeing that the development of operating systems is becoming something that is very softer in the corner. So today I want to talk a little bit about what I do. I'm Desnes. The name is a little bit different. Mom and dad's fault. Who am I academically? I did a master's in parallel computing, and now I took during the pandemic, I was finishing Netflix. So basically, I watched all the good shows, and I was starting to watch bad shows. So I decided, hey, let's do a PhD. Why not? It's online. And afterwards, I also had 2 kids, so now I don't sleep at all. Professionally, I worked in Linux for about almost a decade now. I started working with PowerPC, and now I work at Red Hat, and I am the USB and Thunderbolt subsystem maintainer for RHEL. So, what I got for us today? Basically, I want to talk about how Linux got to the point that it is nowadays. How to work actually with kernel development. This is like, I'm looking for undergrads, for juniors, for people that never even compiled a kernel. I want you to leave this presentation at least having that idea and at least knowing a little bit more.
Sorry to interrupt you. There is some problem. I think
The what?
The screen
Looks fine to me.
Yeah, it's not exactly what is appearing for some reason.
No, right here. Oh, right there?
Yeah. For some reason.
Oh.
So. Yeah.
What I do? What I do?
Camera is right?
Ah, tá, mas tá vendo que a tela aqui tem.
Ele ligou, não foi a tela.
I think it is as a second monitor.
It is as a second monitor. So, do you want me to change? I can maybe. I'm using the PowerPoint.
Você tem alguma coisa escrito HDL aberta?
HDL, no.
No browser?
On the browser? I don't have a browser.
You have 2 screens, another screen is being recorded.
Alt tab.
Não, não é isso.
If you want, I can try to use the PDF. Does the PDF work?
The screen's not mirroring.
É outro. Peraí.
Oh, okay. Then I don't know what to do.
Isso aqui, ó. Vamos aqui.
Good. Good.
Oh,
Good. We are good.
We are good?
Go ahead.
All right. Thank you. Let's go back.
OBS Studio issue. For some reason, it's freezing the images.
Uh-huh.
It happened with the camera a few times, but now it happened with the screen. So
Bugs follow me, man.
this was actually when you open the browser with bytes. So it was bytes in the screen, and I was okay. So that's bytes. So it's freeze. So I just activated again. It's working. Go ahead. Sorry.
All right, no. Bugs follow me everywhere. So basically, so as I said, I really want to show a little bit about work, and I also want to show a little bit about debugging, but a little bit more than at least what we see. So I have here another laptop, which I plan to do a little debugging of USB.
So maybe, let's see if it can be interesting. I want to skip right over this, but basically how Linux got here nowadays. Before it was a complete mess. Like everybody had different ISAs, everybody had different protocols. And back on the 70s, on the 80s, instead of explaining this, I really recommend, I don't know if anybody already watched it, there's a cool film on YouTube, Pirates of the Silicon Valley. No, there we go. So if you don't have anything to do tonight, really watch that, it's very fun. And basically it tells all these stories about how technologies fought each other, and especially how open software began to have a feeling what we're seeing nowadays. And with all this fight of trying to create standards for protocols, companies like IBM, Apple, and everybody try to kind of go ahead and go to this finish line first of becoming a pattern for that. However, there were some fights. I think that I'm really sad is that in the past there weren't anything like Twitter. I really wish there were Twitter or something like that, so people would actually see what happens instead of like you going on this person's profile. People used to send letters. So basically, if there is some, I put two things that I really love of these letters, like people fighting through letters, and there's the famous Bill Gates quote that he was really upset because he was seeing that the hardware was selling by tons, and it wasn't, and he wasn't receiving as much money as his bank account, and the reason was that because people were starting to open software, share software. I think it was Ken Thompson, the guy on the left on that page, that he used to work in the mainframes and stuff, and he used to send patches under the systems. So this is an amazing story. I don't remember where I saw this. So you used to buy this huge mainframe and and you received whatever IBM bundle on it, and under of it simply had these huge floppy drives from Ken with Love. And basically it were patches. People were sharing already the idea of open software. And back then it's this weird times that Unix was really the pattern for other development and pattern for operating systems of big machines. The Unix version of it, the 6.0, was around 20K. And this nowadays it's like $80,000 for almost $80,000 just for the operating system. And up to one point there was when the hobbyists, what Bill Gates used to say, started growing, and people started to wanted to make more. So you have this computer, but hey, maybe I can have, I don't know, some other tool, some other software that it might help my job. So that's when browsers started being made, the languages, oh, I don't like this language. Maybe this language does not fulfill my needs. And the weird thing was, hey, but how can everybody was, if you have in one hand, in one corner, you have Apple, you have Microsoft, you have all these companies fighting to who owns what. The software is mine, it has to be mine. I invested money on it. You had people like Stallman and other people fighting, no, I want to make software free. I want everybody to use it. So that's when the copyleft licenses started to appear, like GPL, MIT. And in one of it, if you have all these hobbyists, but there's also the idea that students didn't have much software to work on. So that's when Thunderbolt created Minix. Anybody used Minix? No?
Everybody using Minix.
Exactly. Anyways, so Minix was a first version of operating system that was cheaper, and it was for students, but again, it was a hobbyist, so it was purely academic, even though it had everything an operating system needs. Nevertheless, the things that, oh, I missed one thing. Minix kernel, the heart of the operating system, it was something called a microkernel, and in one hand, it was robust because you had modules. So you had your drivers, you had your Ethernet drivers separated from I don't know, yeah, the disk driver. Everything was separated and everything communicated through layers and also through messages. So it's like a postman. So if you wouldn't do a syscall like we think of it, you would actually send a message and that message would be sent to the kernel and so on. So in one hand, you had this, which is more academic. And for instance, if your driver got killed and it crashed, it automatically was going to go back up again because it was just that part of the code that died. So that's when Linux came on. And I think that the connection with Linux is that, I don't know if a lot of people know, that he started Linux on the Minix mailing list. So basically, he sent an email, and I love this email. This is his first email saying that, hey, I'm doing a free operating system. It's not going to be as big. And what happened was, this was 1991 when he was just like a student. And almost 10 years later, his code bumped to infinity. Nowadays, we're talking about 30 million lines of code, this huge independent and distributed system that everybody kind of uses now, but they don't kind of know where it is because everything is so API nowadays, AI and all that stuff. So this is just a little bit about the architecture that I was just mentioning, the drivers and how what was the paradigm shift? Because now Linux created his monolithic kernel, and the monolithic kernel was it was way faster because there wasn't all these messages. However, it's more prone to errors and bugs and so on, because instead of crashing just the driver, now you can crash the whole thing. So basically, it's the trade-off of security and speed, and it's like you have to make it when you work on IT and all this stuff. I will not get in much of detail here, but basically, I really hope to give the idea of monolithic and microkernel. However, Linux had just his kernel, so he ported a little bit. He ported the bash, he ported the GCC. So he needed a little bit more to create like a fully operating system like we know nowadays. So basically, that's when he connected, and that's why you have some people in the Linux world that they don't like. They don't like to say, "Hey, this is not pure Linux. This is GNU Linux," because you also use other packages that were not developed by Linux himself. And that's also when other companies started going in the picture. So you had SUSE being born in the 1990s. You had Red Hat as well. And later on, you had Canonical. Nowadays, probably most of you already run Ubuntu. So you already run an operating system from Canonical. A few, maybe Fedora, OpenSUSE. Anyways, this was born all at this time that people started to see that Linux needed support. So basically, now you're changing the scenario that you're not just staying with hobbyists anymore. You're making companies that they're running data, they're running workloads. Banking is already growing at this time. So you're starting to have the necessity of having supported operating systems. And also you had the hobbyists. It's really fun. Like anybody heard about Windows Refund Day? That's when actually people went into Microsoft's headquarters from asking for a refund because they didn't want Windows on their machine and they would have to pay for it. So in order to, it's something that is very fun. Watch that video that I mentioned. Anyways, and now what is Linux now? Now Linux is money. It's a lot of money. For instance, Red Hat, with a little mixed feelings, IBM bought Red Hat in 2017. I remember that in Brazil, like it was on the second term elections. It was on the day of the second term in the 2018 election, and people were like talking about the parties and whatever the politic views, and like we could, at least myself, the news for that day was not that the president got elected. The news was that IBM bought Red Hat for $34 billion. That was the news for me that day. And nowadays, you have these ecosystems like, I found an article saying that Red Hat touched more than $10 trillion of revenue in 2019. I think it's a lot of money. But why would a company invest in something that they don't own? It's a very, I really think it's a question we need to make ourselves. Basically, is that since the code is open, you have confidentiality, you have integrity, and you have availability. You have more people looking at it. So instead of, sometimes like if I'm fixing a bug in RHEL, somebody from Debian might get that patch and might also fix a bug in their operating system. So it's, even though it's free, it's open source, like there is a community that people work separate and together at the same time, even though they're competitors. So it's a really nice environment to work at. Where can we find Linux nowadays? Everybody here probably ran Pix. So Pix is actually, it runs in RHEL. It's all the OpenShift and Ansible and everything that Red Hat can offer the best. The voting, whoever vote, when you vote, you're actually running Linux on the voting machine. It's UNix. It's a compiled version of there. I don't know much about it. There was the supercomputer that I had the privilege to work back in the days with Leonardo and everything, the Summit. And if anybody posted a patch, you got to prove it in the Linux kernel, I think up to 4.12, if the aliens ever get a hold of the Ingenuity, the helicopter on Mars, you have your name there. So your name, if you had a patch in Linux by I think 4.14, it runs. I think it runs RHEL 7. I don't recall. But anyways, so basically it's everywhere. Cool. Anybody doesn't know what a patch is? Don't. Git. Everybody use Git. Everybody. Okay. Cool. Let's skip right this. So basically how Linux works is if you find a bug, you can submit. Basically in this distributed development, we overuse something called upstream development and downstream development. The upstream development is when you actually have a bug, it is on the Linux source code, and you found that you have a solution for it, so you're going to send that patch in mailing lists through email. Yes, we still use email. And there is these very experienced maintainers that are going to simply say, hey, this actually works. This is something that it's buggy. I need, so they take your patch in, and this kind of grows all the way up to Linux himself actually doing a pull request of all the fixes. So this is the upstream part. But this is pretty well known. What people don't see much is what happens downstream, like how the operating system is actually developed. So basically Red Hat says, okay, I'm going to develop a new release. I'm going to develop the RHEL 9 releases. So they're going to rebase the code. So basically they take a snapshot, they take a picture of that source code. And afterwards, they're going to simply update it. So whenever there is while the development is actually happening, if there is a CV, a common no exposure, a security error, we're going to pick out all those patches in, and we cherry pick them. And why we do that is because simply customers, like imagine if you own a bank or if an oil company or whatever, you need to have security, you need to have all these fixes. So that's what you're paying the support for, even though it's open software, and especially now because Red Hat even made the source code open through the CentOS stream and all this stuff. You can find the kernel code on GitLab on the web. Wasn't like this in the past. But that's what we provide. We provide integrity, security of all these vulnerabilities that you can think of. Another thing, has anybody, well, how can I say? Has anybody built a package, a Linux package? Cool. So basically, what you have is, what companies do that, as I showed for the kernel, they do for all the packages. So if you have a compiler, if you have an editor, all of this source code is packaged and bundled, into these little packages, and also there's the package manager on every operating system. Anyways, for if you don't know, this is the basic code of a package. This is as for rel. This is a spec file. And basically on it, you're going to say, hey, this is the arch that this is going to run. It needs this. Here I have, in order to install, I need to have this folder. There's this license, and you put a change log for the patches. So this is what you actually receive if you open the source code of a package. But hey, how do I actually build a package? So if you, does this have a pointer? No.
Yeah,
So
yes. Red button.
Left?
Red. On the
Okay, cool. Thanks. So basically, let's say you want to build the Red Hat kernel. What you're going to do, you're going to simply install this little package, which is the source RPM. Inside of it, it has a kernel spec file, which is something that looks like this. And simply, let's say if you want to add a patch on it. So you created a patch, you want to test a package version of your patch. So this is the commands that you have to run. He already has the slide, so if you ever want to play around with this. So this is the part of building a package. But let's talk a little bit about debugging. So debugging is not as trivial because, first of all, you need to have patience, you need to have perseverance, and read the freaking source code and also the specs. Why? The more that you get acquainted, not only with the things that should work and how they work and whatever everything in the kernel, like if you're going for the USB and all this front, there is the specs. If the buses, they have specs that you can follow, and everything is free, and you can download and you can study them. And it's a little, it's that feeling that you can't really describe. It's like, the more you understand, and finally when you find a solution, it's really amazing, at least for me. But let's see, what I want to do today is actually show some tools and tweaks and stuff that can help you out if you want to start on this journey. So let's see what I have here. Does anybody know what this is?
Menu config.
Yes. So basically, I put here the basics that you need to at least compile the kernel. So this is a thing that I wished I saw on my day 0. Oh, wow. Okay, so basically, in order to compile the kernel, this is the main commands that you're going to use. And one thing that the companies, the operating system companies do, they kind of do this for you. So that's why what Red Hat sells, what Canonical, what they create a pre-config kernel that is able to support most of the common devices, drivers, and so on. But how can I save time? Yes, saving time. It's really important. So the less time you will wait compiling and the more time you spend debugging, it's important. So basically, for instance, on this laptop right here, in order to compile the kernel, it was around an hour. So if I try to compile it again, it's faster because everything is already pre-compiled, of course. But sometimes I think, at least myself, we think much of it as a recipe. So what I used to do is like, hey, I did this change. Okay, this change, let me compile this change. So I wait, I study, open the browser, do something. And by one day I was like, I'm changing a module. Why am I compiling the whole thing? So basically, there is this other, you can save time even on working and studying. So instead of, let's say if you're, the configs that I showed you, your modules can be either built in the kernel, or they can be just like if you can think of a shared library, they can be insmod and rmmod. You can attach it to the kernel. So, for instance, if I'm working in just a part of a driver, I can simply compile just that driver, unload it, and simply load it again. So this is going to save me time. Instead of waiting 3 minutes for every time, I can do this kind of instantaneously. Demesg, if you don't know, it's a ring buffer for all messages from the kernel. So every subsystem on the kernel spits out all messages. So that's where we start when you have a bug or anything. You're going to look at its demesg. There is, of course, print K, which is the first instinct of everybody. So let's print out here, there, this variable, that other variable, and so on. It is helpful, yes, but it's not as effective. So that's what I'm trying to show today. There is also what I consider print K on steroids. There is hex dump, so you can simply, instead of just printing one variable, you can simply dump some part of the memory afterwards, after a pointer. There is warn on, bug on warn. So these are also some macros on the kernel that you can use that they're going to print the stack for you. Sometimes you have a message like added a new device. So you want to debug all the way up to the when was the first intent of that call. So you can put warn on messages if you want to see the whole stack trace. Again, every time you do this, you have to compile the kernel. But what I'm trying to see today is if we can think of ways of not having to compile the kernel as much as least as possible. So another tool that I really like to use is dynamic debugging. So the first instinct is to, as I said, put to print K everywhere, xdump everywhere. But the kernel already has a lot of debugging messages in it. You have just to enable it. And that's where some people don't really see this. At least when the first time I noticed, this is very easy. Why didn't I do this before? Basically, you change the boot options of the kernel. You can add, for dynamic debugging, there is this flag that you can add a few modules. And every special print message, like devinfo, every subsystem kind of creates their own print K messages. So basically, just by adding these flags on the booting of the kernel, you're going to have way more debugging messages. So this is really helpful. GDB, you can use GDB as well. When you install the kernel, you have a system map flags that they're going to give you the symbols of your kernel, all those sections and so on. So if, for instance, if you want to see the assembler code that is on the text section of the kernel, you simply can say, hey, GDB Red Hat provides this as a debug info package. So you install this debug info package, and afterwards you have the symbols. So you can use the symbols to see the assembly. Hey, let's expand this macro so I don't have to do this all the time. I figured it out. Another tool like that is ADDR address to line. Basically, you use the VM Linux compiled of the kernel, and you can find out which, for instance, let's say your kernel crashed, you have all that dump, and you can get that address, and you can say, hey, where does this address, where this failed? So you can get that address with the VM Linux, which is the kernel uncompressed, and you simply figure out, oh, this comes from, this file, it comes from the core.c or whatever. This is very helpful. Another tool that I think it's very handy to always use is KExec. Anybody use KExec? Cool. What KExec does, it simply ignores the first booting stage of your computer, your system. So instead of going through BIOS, through all the bootloader, through all the stuff, you simply reboot from your kernel. So let's say, but hey, it boots really fast on my laptop. It boots like in 30 seconds, 1 minute. But when you go into servers, there are some servers that they can take like 40 minutes to boot. Or like you're not going to wait as much if you simply boot the kernel of it. So this is really handy. And this was also a tool I wish I saw on my day 0 of debugging. On top of KExec, there is also kdump, which is very useful. Kdump, anybody saw? Cool. Kdump is basically, it's if you want to use the sport analogies of the American football, like you're almost losing the game, so simply you're gonna throw a Hail Mary on it, and basically the kernel already noticed that it's gonna fail. It's about to crash. So instead of waiting for that crash, what it's gonna do, it's gonna kexec into a different kernel that Debian, RHEL, Fedora, everybody kind of provides it, and it's the kdump kernel. So it simply is gonna fetch every kind of message it can. It's gonna fetch the buffers, it's gonna fetch the memory, it's gonna fetch the registers, everything that you can use for a post-mortem debugging. And on most of modern operating system, Linux is already, by default, it's already set up. In the past, you used to have to set it. So it's also known as crash kernel, and you can separate the amount of memory it can has. A tool that I'm really finding having some I'm liking to use, it's kprobes. This is the little demo I'm gonna do right now. It's just it's built on top of perf, and it's a way that instead of compiling, instead of print case, you can do some live debugging. So let's see if we can play around a little bit with this. So let's see. So let's say. Where's that example? The example that I'm gonna use. Just 1 second, folks. So, okay, so I'm right here. Okay, so basically, no, actually, let's go here. Where's the, I'm not, that's not on transport. See, live jitters. Okay. Well, this is the example of the warn on I put, but I want to show the code of. Hold on, let's add a. Let's look here.
If you could increase just a little bit the font size, it would be really awesome.
There we go. That good? So see all these messages, they're not normal USB messages, as you can see. I just added a thumb drive on there, and there's way more messages. This is because I'm using the debug kernel. Hold on, let's put, there we go. So when I add a USB device, you're always going to see these messages. So where does this come from again? I forgot. So this. Nope. Okay, so there we go. It comes from, so I'm finding the message that was on dmask. Okay, so what I want to see, what I want to show is this. Okay. So when I added the USB device, all the information is on a kernel structure. All right. So I want to see stuff in the structure live, but how am I going to do this without printk, without the whole stuff? So there's this tool that I really enjoy using, perfbin. Okay, so I can say, where's the presentation so I can get the notes? So let's say, okay, that's why I'm clicking. So I kind of use perf. I provide perf. I'm gonna say I'm not gonna create a whole breakpoint or other stuff. I just see that this is. There we go. I use perf to simply give me the dislocation, the reference of that pointer in the function. So for instance, if I add this dy, this is from calling conventions. I don't know if you remember calling conventions. So every, on x86, every parameter, like whenever you call a stack trace, so the first parameter is always going to be in the DI register, the SI register, the D. So this is so on for the order of the parameters on the stack. So that's why I got, where's my keyboard? So that's why I got this DI register. Okay, but I don't want to see UDEV. I want to see here, for instance, I want to see the ID of the manufacturer of the USB thumb drive. So I can simply dereference it to the descriptor. So now it shows me the amount that I have to dereference this register. Okay, but this is still not what I want. I want to see the descriptor, but I want to see the ID vendor. So all of this is stuff that is on the structure. So, okay, so it shows me this is what I have to show. So this is what I have to dereference in order to see this. So I use the kernel probes tool. Leo, are you going to be mad if I spend a little more minutes? I'm going to need maybe more 5 minutes. So I am going to say I want on this function. And I'm going to use this to see the ID vendor. 16. Okay, so I'm going to put a probe here. Okay. Now let's turn off that thumb drive. Let's insert it again. And all right. So you see, I have the vendor right here, and if you remember it, all we started here was with the new USB device. So I got it live inside the kernel just by the reference structures with kprobes. This is a very handy tool, especially if you wanna, like, if you're debugging something that is inside. The cool thing, maybe I'm missing a little. I got nervous with Leo saying that my time is off. My time is out. Come on, Leo. Maybe I should have started this with where was it? No, it wasn't on the transport. It was on the other message. But I dereferenced twice inside the structure. So I had a structure. I looked at data through its pointer twice. So I kind of did a two jump inside the structure in order to see data. So this is very handful. Let me end, or else Leo is going to be mad at me. Okay, so that was the demo. Okay, just another tool that is very important that I use a lot is bisect. Anybody bisected code already? Okay, cool. So you can either bisect the code itself. So you simply say, hey, or you're on Git, you say, this used to work on version 6.0 and now it fails on 6.1. So basically it's going to do a binary search inside the code. But you can also do this in my daily days, in my daily activities. I do this with packages. So sometimes the customer comes to me and say, hey, this used to work on kernel 418 something .2. So now I have to bisect all the way to 200. So you can either do this if I cannot provide the source code to the customer's machine. So sometimes I have to do this kind of literally by hand, by since I'm working on downstream on this part, so with the NVRs, I kind of figured out where the issue came from. Maybe next year I might try to show some other tools, I don't know. There is CageDDB, which is also a way of debugging live. You have to use two machines, and you kind of make one as a master and the other one as a slave of that machine, and you simply, you're gonna put breakpoints. You kind of work the way that you do with GDB. There is Valgrind, which is also a tool that is good for profiling, finding memory leaks, and all this stuff. Wireshark, that you can work on networks, and it's very helpful to look at this information. So basically, the idea that I try to bring to you is working with kernel is very fun. You can actually go a little bit beyond simply print K. You can actually have other tools. You have to invest a little bit on learning how they work, and after you get a full range of them, knowledge by you, you can things started being very clear. For instance, I showed the registers of the syscall of x86. I kind of already remember all those registers because I do this a lot. But anyways, this was my talk. Thank you very much. Sorry for going over. Questions, hit me, please, not in the face.
One question for Desis.
Yeah, I'm just wondering what the performance overhead of, especially K-Pro, looks like. Because, like, if you look, for example, at the sysblock reports, especially for like unpluggable devices, unpluggable risc-v, a lot of those are like race conditions, right? I was wondering if there's like any.
Well, I haven't hit. Good question. I haven't hit any of those myself, but since it runs on perf under of it, at least I think that the whole structure of perf kind of worries about that. I don't know, handling the stuff with spin locks and all that stuff. So I at least myself, I'm putting my chips on perf.
K-Pro uses trace points, right?
Pretty sure, yes.
Yep. Trace points are very, very efficient. They are per CPU structures. You just save the data that you want exactly to print. And there is this other structure that at some point will print the data and the message. So it's pretty efficient in like memory that's using and also in printing. So by tests, like in real time, it adds close to none of performance issues. So it's pretty cool.
Or you can be a believer like I am.
Okay, thank you, Desis.
Thank you. Thank you. Come work with operating systems. We need people.
So next we have Ellen from Collabora talking about kernel CI.
Hello, everybody. So welcome to this talk regarding kernel CI. This is a presentation based on slides from Gustavo Padovan and Don Zikus. They are preparing this talk for Linux Plumbers till next month. So I picked up their work in progress slides and added a few things. So I'd like to thank them. So my name is Ellen Koike. I'm a senior software engineer at Collabora, and let's talk about kernel CI. Okay, so this is the outline for today. I never know what to look. So let's talk about the kernel CI project and its mission, the Linux CI ecosystem, the audience of kernel CI, the current focus on quality, ways that you can interact and benefit from it. We'll see a demo also, and conclusion, call to action.
So, Ellen.
Yes.
The HDMI is complaining that content is protected by HDCP, whatever is this.
It's a strong protection.
Yeah.
I don't know what it is.
Yeah, you need to change the.
Maybe download the presentation.
Otherwise, you have to present in another one.
Another computer?
Yes.
You mean?
Or not have it live streamed, the screen. No, it's necessary for the people who are watching on YouTube, right? Computers. Yeah.
Yeah, otherwise it's not going to be recorded.
Okay, so yeah, let me send you the link then. And I'll send you the link of the demos. Hopefully they will work. Is it the problem of presentation or of the machine itself?
I think it's here. Okay, so let's get back with proper screen.
Okay, should I restart for people?
No,
or
because
can
you're just in production,
Okay.
So that's okay. And I was showing this screen with you in the video, so I was just going to switch to the slides because you were going to talk about something that was more specific.
Okay,
so,
awesome.
Yeah, just continue.
So we just finished talking about the outline, so let's start with the content of it. So what's the mission of the kernel CI project? So the mission is ensuring the quality, stability, and long-term maintenance of the Linux kernel. And this is not just about the code. When we talk about testing in the Linux kernel, we are also talking about a cultural shift. So there is this nice phrase. So above all, there's an ecosystem behavior challenge ahead. It's not only a complex technical challenge, but for kernel testing, a cultural shift is necessary. So in the community, so in the kernel, we have several subsystems. Each subsystem has their own culture, and most of the time people just test on their own machines, and when they send patches, people believe they tested, then the maintainer is responsible for testing it again, and nobody knows how the maintainer is testing things, so you just return back to you saying it's not working, and then you have no idea how he reproduced that code, and you need to clarify and check how then to reproduce the bug and try to fix it. So this is the current culture. So that's something that we would like to change a bit. So test and validation tends to be internal and closed source. In several companies, they do their own test infrastructure. But open source software should have an open source testing and validation that we can share with the community and everybody could profit from it. The kernel community should keep evolving upstream testing and integration to achieve the product level quality expectation of industry. So the kernel CI goals today is, as I mentioned, ensuring the kernel quality, stability, and long-term maintenance, but also consolidating Linux kernel testing and all this integration with testing. The kernel CI project acts as an umbrella for projects that fit these goals. So we have working groups and also a definition of standards. It also manages resources and core test infrastructure that's available to the community to use. And the kernel CI project, as a Linux Foundation project, has resources, so it can sponsor key initiatives that aligns with the kernel CI goals. So as I mentioned, it is a project backed by the Linux Foundation, and those are the companies that are members from it. So we have the Civil Infrastructure Platform as a primary member. We have Collabra, we have Google, we have Microsoft, we have Red Hat, and recent joined Texas Instrument. And as a general member, we have Bailey Breeder. One of the ambassador of the kernel CI is Greg Krohartman, which is like the right arm from Linus, I would say, or like one of the biggest people in the community. I think that if Linus is hit by a bus at some moment, I think Greg will pick it up. So he mentioned this. So kernel CI is the place where testing needs are consolidating for the entire Linux kernel ecosystem. As a kernel subsystem maintainer, reliable testing is important in catching regressions and bugs in new code sooner before it hits released kernel. You should consider joining the kernel CI to help collaborate on the unification of the testing efforts to ensure that the kernel community can keep developing and maintaining the code base which the world relies on to be stable and secure. As you might know, Windows wins in desktops, but in servers, and basically is Linux that runs. Even in Microsoft Azure, they have Linux running there, which is quite interesting. So our audience. So the kernel CI is meant for maintainers, for upstream developers, for hardware vendors who want to ensure quality of the Linux kernel on their hardware, product makers as well, the same logic. They can they request testing to kernel CI, so they can request or add their tree to kernel CI, so tests will start to run on their tree. There will be, this is not implemented yet, but there are plans, ways where you can request something to be tested in kernel CI. So we are planning to have a command with hashtag there that and patch that you can type and request that patch to be tested. Before test command as well, since before is being used by most developers nowadays. Maybe a button in Patchwork UI where you can go to the patch and request the test there, and also request testing in your own GitLab CI pipeline. Also, people can add and improve tests there. They can improve the test quality, engage with the test development, track the expected tests that the ones that we already know that should be passing, the ones that we know that is failing and it should be fixed. They can also fix the bugs, and also add testing gates to the process. And also, they can evaluate the results. So people can receive email notifications, can use the web dashboard or patchwork to visualize the results, see if everything's okay, see if that patch is good to be integrated in the kernel, be merged. They can pull results from an API, and they can also do some other integrations with tools like P4 that would fetch those results, check if everything is fine before submitting. So this is the overall architecture of the kernel CI as a whole. Let's go together through every box here. So first, we had this confusion regarding the kernel CI project and the kernel CI software. They had the same name, but now so the kernel CI software was responsible for building the kernel, dispatching tests to the boards, and so on. But since this was very confusing, we renamed it, and now kernel CI is everything, is the effort. And the software is called Maestro. So Maestro is basically the orchestrator for tests, which is, now we can separate what we are talking about easier. So Maestro, it's a bit small here. I'm going to read it for you. So Maestro is basically responsible to store the test specifications. It knows how to submit the test, how to connect to labs. It watches a few trees that are registered, so it keeps doing the checkouts of the tree, checking if there are new updates to the tree, and if yes, then dispatch tests. It knows how to build artifacts, how to generate test events. And then we have a full ecosystem that's connected to Maestro that can subscribe to events generated by Maestro. So the most important one, I would say, that's core in kernel CI is the kernel CI labs. Today they are the same software, but ideally it's separated. So when new tests arrives, the labs, the kernel CI labs identify this event and dispatch all the tests to what we call labs around the world, which is a room with a heck of different devices there that you can that people build, so with different kind of machines. So if everything goes right, I think we'll have a risc-v lab probably in here. Awesome, that we could be able to connect to the kernel CI. So those labs connect. So there is a software called Lava. Lava is a standard way that you can do those lab builds. So the kernel CI knows how to communicate with Lava Lab, so this is very easy to integrate. But there are a few people that decide, I want to use Lava, I will do it my own way, and they make it available an API. But we say, okay, let's connect to your lab, and we connect it anyway. We also have cloud providers, so to be able to run tests that are not specific to specific devices or platforms. So there are a few sponsors that provide us credits on the cloud that it can use, and other labs that are available out there. So we also have in the ecosystem other CI systems that can subscribe to the event and cross the data from here with what they have, for instance. So we have 0-day from Intel, we have CKI from Red Hat, we have Sysbot, maybe your CI system in the future, and could be also a firewall CI system. from like a closed version of CI system. Some companies need it, and so on. Right, so this is for testing. Now, we have an interesting part of the architecture called KCIDB here. KCIDB is basically a huge database that people can send their testing results. So Maestro submit the test is run in the labs, it comes back, and then Maestro sends the results to KCIDB. All those CI system here also can submit results to KCIDB, so this is an open database that any CI system can connect. There is an API, there is a definition of which fields, and this is always under development, which fields you can submit to it. So it is not just a database, so it's based on Postgres in the bottom, but when it receives data, there are a few validations that it performs to check if the data people are sending here makes sense or not. And also it do some sort of like queuing, so it manage the throughput of the database, and also it do some sort of post-processing. So here we are doing a lot of development actually in post-processing. One of them is regarding aggregating similar results. So if one of the CI system submits a failure with all the attributes that I'll show you later, like branch, which platform it was, which compiler it was used, and let's say that other CI system also submits the same failure, then there is an intelligence here that will check this and aggregate and to say this is a single issue, and those are all the incidents. So this is very nice to detect regressions and to detect, okay, this happens once more, but this is something that it's nothing new, right? We are tracking those. And from the KCIDB, we have the web dashboards as well, that you can view the results, navigate through the data. The demo will be about this part. And we also have a few other tools for the maintainers to query the data from KCIDB, to command Maestro, to do bisections, and so on. So this is basically the whole ecosystem. KCIDB can also send notifications by email, depending on the scenario of the people using it. Right, so let's talk about how you can interact with the kernel CI. So what you can do today, so it would be really nice to have all those features connecting with Patchwork and B4 and so on, but we are not there yet. But we have a few things today. So today you can add yourself, it's all open source, you can go there and do a pull request, add your tree, to be watched by kernel CI. So kernel CI will start dispatching tests to your tree. You can even define which platforms, which kind of tests you want to run on top of your tree, which ones make sense or not. Or you can just open, pull an issue on the GitHub project, and our team will check and add it to you. You can also add or request your lab to be integrated in kernel CI, so more platforms to test the kernel on. You can also view the results on the dashboards. You can implement or request to receive email notifications in the format that makes sense to you. So there are a few different use cases. When we have a tree that is supposed to be mostly clean with no errors, then it's much easier to submit notifications, because if you have one more failure than before, then this is probably a regression. But if you have a very unstable tree like Linux Next with tons of failures, then it doesn't make much sense to submit an email and each new thing there. So it depends on the maintainer on the tree how people are tracking things there. You can submit the test results to KCIDB if you have your own CI system, if you build your own pipeline, let's say on GitLab CI, you can submit there. And you can also, of course, contribute with coding in any of those tools. So dashboards. We have a dashboard for quick sketch and customized views on Grafana. Does anyone here knows Grafana? Nice, lots of people actually. So Grafana is a UI that you can build, that you can connect to a database and build panels, graphs, and extract data. So it's very interesting for, let's say, I want to view this data like in this particular way, so we can go there and build a panel with the graph that you need with the data that you want to track. And we have an official dashboard that's actually work in progress. Is anyone here from Profusion? That works to Profusion? No? No? Okay, so Profusion is basically a company in Campinas that they are building this dashboard to kernel CI, and it should be released by Linux Plumbers Conference, so at the end of next month, and we are really anxious for it to happen. So, time to a demonstration. Let's hope that everything works. Is the size okay?
Yep.
Awesome. Let me sit here. So this is the grafana.kernel.org. This is the current main board that we have. So here there are a few filters, so you can select which CI system. There are a few of them, so we are checking Maestro. We can check the tree, so there are a few trees registered there already. We are checking the stable RC. You can select the specific branch. You can select a specific test, so let's just take a look at the boot test. You can select a given platform, so this is just saying all, let's see all. You can select a given configuration file that the kernel was built, and also a data source. So this dashboard is collecting data from the kernel CIDB, so KCIDB project, and it has two data sources there, one for production and one for playground. So if you want to start submitting data to KCIDB, you can start playing with the playground, and once you figure out all the fields, then you start sending to production. So this is a really nice way to get started without fear of doing anything bad and messing up with the statistics. So here on the top, you can select the time frame that you would like to analyze the results. So there's a nice documentation here that you can expand. So let's see this. So this is the overall number. So in this date, last Sunday, I believe, we had, for stable RC, we had 11 checkouts of the tree. We built 279 kernels out of them, and we executed 44,600 tests. So yeah, it's quite a lot of tests that we run. Here are the overall the results just for boot tests. So most of them is passing, 4,251, but we have a few failures, a few ones that were not executed, and a few errors. So the difference here between error and failure is basically error is an infrastructure error, something that we detected, let's say, the cable wasn't connected well, or the internet went down, and we managed to detect it, so we report it here. Here we can see per tree, so build failures per tree, so we can see Android is failing most. Stable RC, we have 10 failures. We can see overtime. We can check the test failures per tree in the period, so here's just for boot. We can see the stable RC here had 177 errors, and also over time. Then this section is for build failures, and we can check in the stable RC tree which ones are failing. So we see these two branches have a few failures. We can check by per architecture. So we see that risc-v has a few failures. Okay. And per config. And then you can check the list of all the builds. So you can filter here. Here I just filter by failure, but you can see all of them. You can check the filter a few other fields. So per commit hash, per architecture, compiler, config. Here we try to summarize the log line where we see the error, but sometimes we don't manage to pick like the right line that is really useful. And then you can click in one, and it should open the details of that specific build. If internet helps me, yeah. So you can check all the information of that build, the branch, the repository, the history, commit name, status, architecture, the log excerpt as well, and you can check the full log here, and the output files and some other fields associated with the build. So this is for the builds, and we also have for the test. So here we are just checking boots again. So per branch, so we see that Linux 6.10.y is failing the most compared to the others. We can check which type of test. We have most errors. We have a few different boot configurations. So this, for instance, is from boot testing by NFS and so on. So you can check which one is failing per architecture, per config, per platform. So we have a bunch of platforms. We are only showing the ones that have some failures there. And then you can check the list of all the failures, and we can filter here by fail. And same thing, you can click and check the information of that specific failure and try to debug and see what happened. So this is the overall board, but I'm going to mention a bit more about it, but we are building an effort to do a specific board for specific maintainers, for maintainers in general. So for instance, here we have a board for codecs. Yeah. So here is the list of commits in mainline master. So to check a specific commit, we can just click here and click on see commit, and it will open this board for this commit. So here we are checking this specific commit, the 3D5 something, where we track only tests for codecs, and we track the number of failures, passes for this device. So the codec people are interested in a few specific devices. So I think they are basically Chromebooks here. MediaTek, mostly, I think there was, mostly MediaTek, I don't recall this one. But then here we can check the failures over time. So we see that they are not changing. So this is expected, but some of them have a few variations. Then we can go there and check. Where is it? It's the last one that I didn't open, of course. No. Maybe it's not in my time window. But anyways, if you see a variation here, so increasing or going down, so then we can take a look and, okay, I need to understand what happened. Let's investigate. So people can click here in the list of failures, and it will open all those failures that it's mentioning in there. So we had 40 failures listed. Then when they click it, 40, and people can click on them and try to investigate what happened and try to debug. We also have the official dashboard that's very work in progress, but I show you anyway. This is the current mock-up, I would say. So there's a list of trees, and you can click on a tree, then you will be able to check builds, boots, tests, so but it's not yet working. Build, boots, tests, information, so this will be more like upstream, more official dashboard. Right, that's it for the demo. So as I mentioned, we have this feature about aggregating issues, which is forecasted to be ready by plumbers. So we are really rushing things to get things ready for plumbers. The idea is we can aggregate the same type of test failures incidents in a single issue. How we do that? We basically we parse the logs, check how similar they are, and we try to match a few similar characteristics, so we can aggregate. Okay, all those errors belongs to the same issue. So, but we are also working on auto creation of those issues and auto matching new nodes. So new build test, new boot test. Check which issue it belongs or if it's a new thing. So we auto match those with the issues. And we call this an incident. So an incident of the issue happened. With this, we track known and new issues, and this provides a better regression tracking. I always forget the button. So now we started this effort called community engagement effort, where we want to hear your requirements. So please tell us your requirements, because we have a team dedicated for you. So if you come to me and say, yes, this will be very useful for me, I would like to watch this tree, I'd like this test to be run, I would like to be notified this way, I would like to have a Grafana dashboard like this and that, to view this data, please talk to us, and I can allocate people to work on that for you. And we are doing that basically because Kernel CI didn't went out. So people are not really relying on Kernel CI at this point, and we want to start this process because we are getting ready to this point. So basically we are searching for alpha and beta testers that can help us to deliver something with value. So yeah, please come and tell me what you need, and we will make it work. So we like to know also which trees you are interested, maybe platforms. We have a person saying that he's an SOC maintainer, so Kevin Hillman wants to see per SOC family the data. So we are trying to make this happen, because SOC family was missing in the case. This information was missing in KCIDB, and we are now changing things to add it there, and so on. So please come to us, and we'll make an awesome board for you with the data that you need. Get involved. So this is the mailing list, kernelci@list.linux.dev. You can also get in touch on IRC, so Kernel CI on Libera Chat. And we also have a community meeting every Thursday, 8 a.m. Brazil time. And yeah, feel free to show up. There's a Jitsi link that's always the same, but if you just send an email or send me a message, I can send it to you. So we'll have more about Kernel CI at Linux Plumbers Conference for those who will attend or will follow over the internet. So we'll be at Halltrack. There will be an evening happy hour. There will be a testing micro conference where we'll talk more about it. Boot time, testing discussion. There will be also a discussion regarding continuously testing in the kernel. so feel free to ping us. And yeah, so we need your engagement and feedback to help you make the CI and testing better for the entire Linux kernel ecosystem. So talk to us, and yeah, that's it. Thank you.
Questions for Helen?
I have one. Are you using like Ccache or something to avoid like rebuilding stuff that is already built and not changed in the patch set?
So the question is if we are using Ccache
Yes.
In Maestro, I suppose, because the kernel CI has also the CKI people from the Red Hat is working with us. I'm not entirely sure, to be honest. I know that in the GitLab CI effort we are, but in Maestro, I'm not entirely sure. I think so, I would guess, because the amount of load is really high. So I would guess, but I can ask and send this information to you later.
Thanks.
Any other question?
Yes, I have one. Do you also track the performance of the test, like how much does it take to boot or run a specific test, so we can know if the kernel is just booting faster on a specific board or it's degrading, something like that?
So the question is if we track performance, the time that the kernel takes to boot, for instance, on specific boards and so on, right? We had a request for it actually from the real-time community. So the maintainer, who is Daniel Wagner, asked this week. We don't have it yet. We have a few there with the duration of the test that we can start use to build dashboards for performance. We have a few examples how to do that in Mesa CI because they also use Grafana. So Mesa is the user space part of the graphics stack, and they do track performance. They use even games, like they collect information from games, and they get the objects, the rendering code for one frame to the other to check performance, and they have a board that they track that. So maybe we can use the same view, we can get some ideas from them, but we should be starting working on that soon.
So the Grafana dashboard is kind of like a centralized platform where you show the data from the KCIDB, right? Is there a way to access the raw data from KCIDB in case anyone wants to build their own dashboards or just run their own data analysis on the dashboards themselves, the databases themselves?
Right, so the question is the Grafana the central way of viewing the data, and if there is another way to get access to the dashboard, to the data directly, so people can build their own dashboards and do their thing. Yes, so who is the maintainer nowadays is a Red Hat person called Nikolai, and you basically go there and ask Nikolai for an access, explain what you want to do, and he will give you credentials. And that's it. But if you want to build a Grafana dashboard, it's probably easier to just be add your user to the Grafana, and you can have your folder there, and you can start build your views there.
Right. What exactly? Well, I don't know if it's like maybe a too broad a question. Maybe follow up on that later. But what exactly is the process nowadays for adding a new lab to the current CI infrastructure? For example, there was 5 lab that there's been some talk about having what would be the process to add a new lab?
Right, so the question is, how would be the process to add a new lab, to connect a new lab to the kernel CI, right? There is a documentation available in the code about labs, not about devices yet, but for labs, yes. Basically, you need we need to understand your lab setup, right? If it's a Lava lab or is any other type of lab, and then there are several configurations files. You can request it to be connected, or you can go there and code yourself all the configurations, submit a pull request, and then it will be connected. There are 2 instances of the Maestro as well, production and staging. So probably first we connect to staging to check if everything's fine, if we can submit, use your lab and submit a test, and then we migrate to production.
One more question. What are the requirements for the device to boot and run the CI? Does it need to boot from the network, for instance? How do you put the new kernel to run?
Depends on your setup. There is one lab that uses Docker, use everything in a Docker and boot the kernel. It was the Galia lab, if I recall correct. I'm not sure if they are connected to the kernel CI though. I know that they are connected to the Mesa CI. There are a few people that boots over the internet, the NFS, through NFS. Yes, also, I believe that it depends on how people hack. So if you manage to do your configuration and have an API that expose that, it can work. So there are even those SD cards that you can connect with the net, like is a special device that you can control the network that goes to the SD card, for instance, that you can control the rootfs for a Raspberry Pi that you could use, for instance, yes. And there are a few electrical equipments that you can turn on and off the devices remotely.
So there is no strong requirement. You can just create a script.
So basically, the Lava software, you need to code the. So it provides the interface, how people can connect to it and perform the operations, but you need to code how is this board supposed to turn on, how to turn it off, how to submit the rootfs to it, and so on.
You can put extra devices to control this specific board.
Mm-hmm.
I do have a question. I'm not sure if it's out of scope for the kernel CI or what you are doing, but do you have a pretty well-defined build system, like, because then you can have variations of the toolchain if you are starting like this is building on Debian, that one's building on Fedora, and things get messy. Do you set something and use for all builds? Do you try to test with others?
Right. So the question is regarding the testing OS, for instance. If we just select one, let's say Debian, in using all builds, or if we can have others like Fedora, like other systems, right? So we don't have a strong requirement. We just need this information to be submitted as well. So we have a field there called environment, MISC, and we need this information to be added there. So for now, I believe we only have Debian, but the Google people wanted to add Chrome OS as well. So they want to perform the codecs people. So they wanted to perform the same test on Debian and also on Chrome OS. So they will submit this test, just have a field there so we can separate where it was executed, so we can debug later.
All right. Thank you very much, Helen. So we have a break now. We will be back in 15 minutes. Okay? Thank you. So let's start again. Next we have Leonardo Braz with Enhancing Linux for real-time workloads with KVM. Go ahead.
Sure. Hello, everyone. Well, this presentation is kind of a recycling of the previous presentation where I changed something that did not quite go as well as intended last year. And I also added some extra things to make it more easy to absorb the knowledge. First of all, from the people around here who knows about real time and have some knowledge about the topic, could please raise your hands? Okay, awesome. Then I will try to go faster in the first parts. Well, the idea is to improve Linux for real-time workloads. And this year I added KVM because we are also talking about that. Well, who am I? My name is Leonardo Braz. I work at Red Hat in the VRIT team. I work mostly with the Linux kernel. I improve real-time, CPU isolation, and guest latency. And as a side quest, I try to improve risc-v architectural code. You guys can find me at Leo Braz at IRC, GitLab, GitHub, and a lot of other networks. That's my usual handle. Well, I will start with the basic part, real-time. Then what is real-time? And I will try to describe that with a very short phrase, which is basically, I need you to deal with this request in T-time, or else bad things will happen. That's the main idea of real-time, okay? Now the formal description. Real-time is, in computing, is the term that we use for hardware and software systems that subject to a real-time constraint, for example, from event to system response, which is the most usual thing. You have a request and you have to reply in given time or else, right? They must guarantee response within the specified time, which is often called deadline. So you must not miss the deadline or else bad stuff happens. Why does it matter? Well, missing a deadline have bad consequences. So you have a system you needed to respond in this time or before that time, or else bad things will happen. For example, in a hard real-time system, you have that missing a deadline will cause total system failure. Let's say that you have a pacemaker in your heart and you miss the beat, and well, that may not be that good, or else you're in a hospital and you have this machine that is monitoring life, and well, maybe you may not want to miss that deadline. You have like firm real time, which, well, you can miss one and another deadline and it will not crash the system, but that deadline will go to waste. And the soft one, which, well, you may miss and the system will degrade its quality if you keep missing them. So deadline, to be more clear here, is you have a request, you have your real-time system or slash workload, you have a request or event, you have a response or result from your real-time workload, and this response time is the time that you take to reply, obviously. And the deadline is the maximum response time for that given workload or that given system needs the reply. So if you miss that, that's bad, okay? Like I said before, hard real-time systems, you have like pacemakers, robot surgery, well, we don't want to mess with that. Industrial process controllers, also you may like have to stop the pipeline if something, if you miss a deadline, and that costs a lot, so you don't want to have that. And for soft real time, you have something like audio systems and video systems, like you are on a meeting, an online meeting with video, and you lost some packages. You want that to be like as synced as possible, but if you lose packages, it's not that bad. And of course, video games, let's say that you are playing that game and it's competitive and you miss a click, you click and it does not respond, it's not good, you degrade your experience. So that's a way of showing that soft real-time exists around our lives. Well, you want it to respond in a given time. What is the shortest, simplest way of doing this? You have a CPU, you program it directly, you don't add any operating system, and well, you can very easily have this response time very well set on your CPU, and unless you have some hardware failure, you are guaranteed to not miss any deadline if you do that correctly. That's because you don't have operating system to add overhead. But, well, using operating systems is much more comfortable. You don't have to keep implementing drivers. You don't have to deal with creating your own routines. You can use standard libraries and so on. So, yeah, it's good. Abstraction, drivers, libraries. Well, aren't there any OS that are focused on real-time workloads? Yes, there are some. FreeRTOS, Zephyr, RT-Linux are some examples. And each of them has to compromise in some way to be able to achieve real-time performance. Zephyr, for example, has a very simple kernel. FreeRTOS have some weird ways of allocating memory, more complex ways, and it will depend on what are you using. And RT-Linux, for example, this image is better. It just runs a thread with Linux, and your real-time workload goes here, which is bad because you have all the stress of implementing a lot of stuff for your real-time workload. But then you have this VM, let's say, running Linux, where you can deal with network and something that you don't actually need to be real-time. But your real-time workload, you have to implement that on the platform, like in the system of RT-Linux. You can just pick your application and just like the one that you design on Linux and or other operating, and just move it to RT-Linux. It's a different operating system. Well, what about Linux? Why can't we use Linux for as a real-time operating system? It's the major free operating system in the market. You don't have to pay royalties to use it. So why not? Well, it was not planned as a real-time operating system. It's more focused on performance, so throughput. You do not necessarily need to do that work in given time, but it's preferred to use your computing power as efficient as possible, and you focus on throughput at this point. It does not have deterministic behavior. When I say that, I say the one that you just installed, the vanilla Linux distro. True. Sorry, my throat is bad. And well, of course, you are running your real-time workload there, and it can be interrupted by the scheduler or the kernel or anything that's considered more priority, and will cause missed deadlines. So we don't want that. Let's say you're with your surgeon robot and you're controlling it, and then operating system stops because it has to schedule an idle task for some reason. You don't want that to happen because you miss the deadline, and that can be fatal. As one of the major OS availables, it has access to many programming languages. You don't have to be constrained on the language that's supported on given platform. It has libraries, tools. It's much easier to develop and debug code on Linux than it is to do that on bare metal systems. It has extensive support libraries. The source is available. You can change and add some stuff. You just add the things that you need. You don't have to rewrite the whole stuff. Well, but to be able to use it as a real-time operating system, some changes are necessary. The first one is scheduling policies. Well, we have this fair scheduler in Linux that gives everyone a time slice and tasks don't get stuck. Well, but we are running real-time tasks, so we want to run our real-time task first before any other task, because ours is more important. Ours have to deal with the deadlines, right? we have something that's called performance schedulers, such as sched-other, sched-batch, sched-idle. These are the ones that are normally enabled in Linux. They are focused on performance in throughput, not how fast can I reply this, but how many replies can I have every hour, let's say. That's performance focused. But there are real-time scheduling policies like sched-FIFO, sched round robin, and sched deadline. What they do, they raise the priority of your task and make it run first, as the first slide. Sched-FIFO, first in, first out. It all starts with priority. The highest priority task will be run until it ends or until it gives the CPU time to another one, like sleeping. But given the same priority, let's say that you have two tasks with the same priority, you run the one that was inserted first until it's finished, and then it will run the one that was inserted last. Okay, round robin does a kind of different. I mean, the priority part is the same, but it gives a time slice for every one of those tasks to run. Then it runs for this time slice task 1 and then task 2. I have an image here. It's better to understand. And sched deadline, where you have to pass, like, this task has this deadline, so it will order the tasks in order of, like, I don't want to miss the next deadline, so it has its perks. It's interesting. This one here is sched-FIFO. As you see here, it was inserted in this order, so task A will run until it finishes, then B, then C, then it will go to the other priority list, D, E, and F. Round robin, it's a given time slice, so it will go through the highest priority first, so run A, B, and C. A was not finished, so runs again A, B, and C, and so on and so forth until it's finished here. And then you have D, E, and F started. Even though D was inserted like before B, it will run after because the priority level is different. So you cycle inside the highest priority level that has tasks for running, it will like add time slices and keep running until the tasks are finished. And the deadline here, you schedule stuff like this deadline is T plus 0, T plus 1, T plus 3. So then what is the first deadline? Then we will run until it's finished. Then the second deadline run until it's finished, and so on. Preempt RT. What is preempt RT? Stop the kernel, run my task. You have this real-time task. You have the kernel. Kernel has to do stuff. We are not neglecting it. But our task is more prioritized. So we want the kernel to stop running if we have something to do with our task. Give CPU time to it, so we don't miss the deadline, right? It's a kernel option, it's a compile option, where you enable a fully preemptive real-time kernel. What's preemption? You interrupt given kernel, like given task, to run another task which is more priority. Usually the kernel is not preemptible at this level, so this function here this option here will enable the kernel code to be interrupted by user space code. How it does achieve that? Replaces locking primitives that would like hold the CPU for long. It will replace them with CPU like locking mechanism that will allow sleeping. The locks get preemptible, so let's say that you can't get this lock and continue, then it can be preempted at this point. And by changing this, you allow the kernel to be mostly preemptible, except some entry code and some interrupt that are very low level, so you can have a lot of control over that, but that's mostly hardware stuff. How does preempt RT improve real-time behavior? Well, if the kernel can be interrupted, you can interrupt this to run your real-time task. And if you run the real-time task first, the chance of missing a deadline is smaller, right? Because you are trying to give for this task as most CPU time as possible, as early as possible, right? That's an example of how that works. I mean, this is without preempt RT. So let's say you're running your user code and then scheduler goes on, switches to kernel code, and you have this real-time request. You have to reply as fast as possible, but it finishes running the kernel code, then the schedule is out and runs the user code. With preempt RT, what you have is like you receive the request, schedule out the kernel code as fast as possible, and then run the user code. You see that here it finishes running much earlier than previously, right? Like this one finishes running the user code before this one, so it replies faster. Okay, another concept that's very important for achieving a good real-time response is CPU isolation. What does it mean? You say at boot time, don't run stuff on these CPUs. You pass a list of CPUs and say, don't run stuff here unless I tell you so, right? How does that work? You pass this parameter to like the command line of booting Linux kernel. There are other options that also use the CPU isolation to avoid running the tick. I will explain more about that later, but the tick is a periodic interruption that allows the scheduler to run. I mean, you're running your workload, and after some time, your scheduler needs to run, or else like you will starve the other tasks. So this scheduler is necessary at this point. What does CPU isolation change? An isolated CPU that you selected in boot time will not be selected by the scheduler to run any tasks. So how do you use these CPUs at all? You have to pin them. You just say on your command line that you want to run this task on that CPU that is isolated. What happens then? It will run like mostly alone on that CPU because nothing else is supposed to be running there. Also, let's say that we have some housekeeping tasks that the CPU must do to keep running. Most of them can be moved to non-isolated CPUs and thus providing more CPU time to the isolated CPU to run your real-time tasks, right? And this improves the real-time behavior because there are less stuff interrupting our task, so it has more CPU time, so the chances of it not missing the deadline are bigger, are great. This is how CPU isolation is supposed to look. This here, you don't have a CPU isolation parameter. You have all these 4 CPUs to schedule stuff in. So then, well, of course, the scheduler will divide these tasks over the CPUs that are available. You run this command here, you are isolating CPU 1 and 3, which means that you have to run your tasks CPU 0 and 2, which means that the scheduler by itself will allocate all the tasks on those CPUs. And of course, when you pin a task, you can select the CPU where it's going, so you can pin the task to the CPU and it will run mostly alone. Okay, another feature, which is also very interesting, is no hearts full. What we want with that? If my task is running alone on given CPU, don't run the scheduler. Okay, why we need to run the scheduler? We have multiple tasks, we don't want to starve any of them. So after some time running given task, the tick will happen. The scheduler will check if there is not any other task running. And if not, it will continue the previous task. But if it does, it will switch to the other task if it's necessary. But this interruption for the scheduler to check will steal some CPU cycles. And that may cause us to miss deadlines. So, as I explained here, the idea is to turn off the tick if it's just a single task on that given CPU. Offload some other stuff, other callbacks, and it's built to enable it. You have to enable this option in the building of the kernel. What does it change? Disable the tick, no scheduler running for a single task, less interruption, more time to run your real-time task. Right, I'm just trying to explain here, less interruptions, better CPU. Okay. This is how no hertz full should look like on a timeline. You have your user code here and scheduler, and this is no without no hertz full. Scheduler will interrupt your user code, and at some point you may receive a request before the scheduler kicks it, or just after the scheduler kicks it. So you have to wait for the scheduler to finish and then process your request. If you have no hertz full and a single task running there, you have that user code is never interrupted by the scheduler, and when you receive the real-time request, your processing is much faster. Okay, very nice. A lot of concepts, very dense topic. Why does it matter for us? We want numbers, right? For these numbers, I measure latency. What I'm measuring is the highest latency perceived by each of the CPUs in the system. So I will show an average and a higher number. And both of them are the average of the max latency of each CPU. And then the max one is like the highest latency, latency CPU has. Okay? We use cyclic test, which kind of does something, sleeps, and then go back and check if the sleep time was the one that it was requested, and takes the difference and counts as latency here, which is good for checking predictability. OSLET is much simpler. It is just like reading the current time in a loop, and when it gets interrupted, well, you have a delta between the previous time measured and the next one, and then you just subtract them, and the biggest value of this run is captured as maximum latency, okay? StressNG is just to create noise on the CPUs to test if the CPU isolation is working and the scheduling is working, okay? Cyclic test. It was run on a CPU with system with 20 CPUs for 12 hours. The case here is no other workload. We have an average latency of 4.57 microseconds, and the higher one, I mean, from all the CPUs, the maximum latency of them summed, like average, is this value, and the CPU which had the highest latency is this one, 8 microseconds. Let's say that we have this isolated CPUs, that you have workloads on the even ones, and the cyclic test on the odd ones, you still have this latency. Or what does this mean? Even though you have like influence between the CPUs, the latency still keeps very low. Now let's say that you have non-real-time tasks running in those same isolated CPUs, and they are competing for CPU time with cyclic test. You still have like 31 microseconds of latency, which is still pretty low. Now OSLET, okay? With no other workload, you have like 2 microseconds, which means that your user space task, when it was stopped, like you will perceive the latency at most 2 microseconds. This other case here, the higher one is also this, which means that you don't have that much difference between the highest one and the lowest one. The same state, like we have workloads on odd and OSLET running on the even CPUs. We have this average of 2.1 microseconds, and the higher one is 3 microseconds, which is also very low. This is not tested with workloads in the same CPU because, well, OSLET is like reading the time every kind of cycle, like every 3 cycles it will read time. So it's competing. If it's competing for CPU time with other tasks like stress, it won't behave well because at some point stress will have CPU time. So that's not what we want because it will like measure a lot of latency. Okay, what's new in this presentation apart from the numbers? Real-time and virtual machines. What we want is something like this. You have the preemptor RT enabled, the isolated CPUs, no hertz full, and you use these isolated CPUs to power KVM threads, which create n virtual machines, all of them with the same features enabled, like preemptor RT, isolated CPUs, and no hertz full. And we measure the latency on that workload and on that workload running here. Okay, let's just be clear. They are not sharing CPUs. You will have some situation like CPU 3 goes to this one, and CPU 4 goes to this one. Okay, that's the whole idea. Like we have a huge machine with a lot of CPUs, and you have like, oh, those CPUs will go to this virtual machine, and those are going to that one virtual machine. Why? Why do that? The motivation is the same as regular VMs. We can have less computers, more efficient computers, more powerful computers, and not like have at all distributed computers around. You can like focus them. You can migrate them much easier than if you are running like on bare metal. And well, you can have cloud providers providing you a VM with real-time capabilities. And well, it can enable a lot of stuff that wouldn't be possible if the client would need to like purchase and configure a real-time system. What are the drawbacks of using virtualization? Overhead, which adds to latency. You have guest entry, guest exit. Preemption. If you have preemption, it may happen like on host and on guest, which is kind of weird because like the host don't have vision of what's the priority of the task that's happening on guest. Okay. And well, you have housekeeping. You have the kernel doing housekeeping work on both guest and host. Also, if you centralize your machines on a single place, for example, you have to take into account the latency of the network. I mean, the information has to go in and go out, so you also have to take that into account. For this scenario here, this VM, I collected some numbers. You have for OSLET, you have like 14 microseconds as an average of the max, right? And for the higher one, like the CPU with most latency, we have 23 microseconds. It's still pretty low. Cyclic test, same idea, 24 hours running, 8 CPUs. It has an average of, like with stress, both of them with stress, not on the same CPU, but on adjacent CPUs. You have an average of 15 microseconds, and the higher one is 18 microseconds. So for 24 hours, the CPU which has an event with the most latency had 18 microseconds with competing tasks on other CPUs. And that's what my teams work, reducing those numbers so it can be available on for more applications, and we can use that and we can service people with this ability of doing real-time tasks. That's some of my work in the last couple months. Added trace points for scheduled functions. It helps us to find which part of the kernel is violating our latency requirements. Also, avoiding isolated CPUs. I mean, as I said, we want to avoid using the isolated CPU as much as possible. So there are some works that we need to do to avoid doing housekeeping stuff there. Not always is isolated at this point. For the KVM part, we have like RCU, which has to run at some point, RCU core. There is this case where it was running exactly at the point that the guest exits. So we use a new, we propose it and use a new instruction that is a patience, RCU patience, that enables us to note a quiescent state and avoid RCU core to run for a couple milliseconds after the guest exits, and that's time enough to go back to the guest. And I'm currently working on changing the local lock strategy to avoid IPIs. What are IPIs?
you have a processor interrupting another processor to do something. Some scenarios that can be avoided. I mean, it's pretty efficient when you're not talking about real time, but if we can avoid that interruption on our real-time workload, that's good. That's what I'm currently working on. And that's it. I hope you guys enjoyed, and I'm open for questions.
Any questions?
First of all, great presentation.
Thanks.
I would like to know how I would go about using this real-time version of the kernel. For example, let's say I want to replace characters in a F32 with Linux using this way. Is there a way? Is it easy?
Yeah, well, the first thing I would do is like try to see if that platform that they're using supports Linux. That's the first part, okay? Then you can just see if they are they have this real-time version of Linux. If not, you can compile yourself. I mean, support is complex because it may or may not work. But at Red Hat, at least we have those platforms that are like verified and that they supposed to work. Those were used to collect those numbers, for example. After that, you can just port the application to run for Linux, and the application is just as any other application. You will try to work them thinking about real time because, well, your application has to be designed for real time, but you just would have to rewrite it. But it's most interesting if you're starting a new project, right? Because it doesn't make much sense you have a project that's already working to like port it to another system unless you have this necessity, okay? But for new projects, that's pretty good. It will speed up a lot the development time and debugging time and so on. That answers? Okay, thanks.
Going back to what I showed previously, there is the upstream Linux R3. And for instance, if you're using a RHEL, if you wanted to go for RHEL or something like that, you would grab the config of an RT kernel, and you could build on top of that, on top of the upstream tree.
Oh,
So it's already a base ground.
Yeah, if you have, if you want to use RHEL, you have this kernel like ready.
Merchandise.
Yeah. Purchase. Go on.
About the numbers that you showed in the presentation. For example, if I designed an application that it's supposed to be real time.
Okay.
It's easy to measure the same numbers or to have latencies or?
It will depend on the system. As I said, if you are using a system like the ones I use it to, yeah, you can run that will replicate, the numbers will replicate at the system. We are guaranteeing this. Whenever those numbers do not replicate over some threshold, we receive a bug and we have to deal with that. So if the platform is verified, you're good to go. You can trust those numbers, okay?
Just a quick question. You say you want to reduce the delay number, right?
Yeah.
Is there a goal, like a tangible goal, like 10 microseconds? I don't know.
It will depend on the applications. Like say, we have a client that wants to be a little lower than that's our target, okay? But as a general rule, if we can reduce this latency as much as possible, that's better, right? So the smaller, the better latency, right?
Okay. And what's next in the roadmap?
Well,
I think we talked about it a little bit before, like TCP, those stack part.
Yeah.
Is that on the roadmap?
Well, my focus at this point is on kernel. When you say like about user space code, what you have is like there are tools, there are libraries that are specific for like doing network on real time. Okay, for example, you have like the PDK, which is like user space network, so you don't have to rely on interruptions, so it's faster. So you are probably wanting to use this, but on kernel part, I mean, in my vision, that's what we need to do, like avoid APIs. That's the thing that's sucking more of our latency at this point.
Okay.
Thanks for asking.
So going back to the diagram that you have.
Which one?
This one.
Okay.
How do you guarantee that the isolated CPU in the guest will interrupt another guest if its deadline is approaching?
Come again?
So you have deadlines in real time, right?
Yeah.
You have to comply with them.
Okay.
Let's suppose that vCPU number 4 on the VM on the right.
Side, being it on the fixing side, being on the testing side. So anyone here can try to contribute to Debian. And for CVEs that are higher severity, the security team can also choose to release a DSA. Basically, it's a process that they commit the fix for that vulnerability, they build on their own infrastructure, and they make it available for Debian stable or old stable. And then they send an email with all that information and say, okay, if you need to correct this this vulnerability, just do an apt update, apt upgrade, and you're safe. But they put a lot of more information on the DSA, so that's a thing they do. Important to note, DSAs mainly for Debian stable. So be careful if you're running tests or old stable, they don't get patched by the security team. So, okay, so just a quick note about this. When we release a new stable version, it gets security team support for 3 years. So for 2 years, that's going to be your stable release. And even after the new stable release is released, you have still 1 year of security team support. So be careful with that. What security team do when they receive and evaluate a vulnerability fix? What do they do when they see that the package is affected by that vulnerability? Basically, they have 3 options. They can apply the fix by themselves and release a DSA. Usually for medium and high severity CVEs, they do this and they release a DSA. And that goes through the security feed and it gets instantaneously available for everyone. But for minor severity CVEs, they don't bother because mainly are 3 or 4 people doing that, so they can do for each and every CVE that happens to be in Debian. So for minor severity, they feel a bug in the BTS, so the maintainers can do the process themselves, and so they can focus on those ones that are higher severity. But there is also the do nothing. Maybe you can just change your configuration file to mitigate that vulnerability. Maybe it's not worth fixing that vulnerability. Maybe it's just a local vulnerability. You have to be in the same network. You have to have maybe interaction with the user. And we're mainly talking about servers, so yeah, we don't need to bother. And then it's the patch that fixes it is like 10,000 lines code. Are you going to go through all that to fix a minor issue? Like, yeah, maybe not. So usually here you can see the minor issue that was reported. And I have to say that curl, the curl project does a very good job on it. They released the CVE. They also released the commit that introduced that CVE and the commit that fixed the CVE. So it's way easier for us to fix that vulnerability for curl. And also, how do we fix the CVEs? Usually we do by backporting changes to the code. But we have a bit of a different view here because for upstream developers, how do they fix a CVE? They make a new commit, fix that CVE, and that's good. Maybe they will release a new major version of their software. Okay, that's fine. You get a big change log. Or if they are very cool, they can do like a patch release or a minor release for a LTS maintained branch or something. Or they can like release as curl does the complete documentation about that CVE. It was introduced in that version, it was fixed in that version. This is the commit that introduced it, that's the commit that fixed it. And usually they also say, okay, if you're not building with this curl feature, you are not vulnerable, so that helps a lot. Because there is a lot of things that we don't build, so that's pretty cool. But for Debian, we have a very special case that is, we have pretty old versions on Bullseye, Bookworm that were released like 4 years ago. So like grabbing a new release from the upstream to fix those vulnerabilities, it's not an option for us because we are going probably to break millions of servers around there if we like grab a new version of curl and put in there. So we need to backport these patches and make a new Debian release only with those patches to fix that vulnerability. So meaning that's our job. And how does this process work for us? Usually we go on the vulnerability management lifecycle and all that. But you have to discover that, evaluate the vulnerability, fix it, verify if you really did fix it, and then monitor to see if you didn't break anything. So how would we go about it? We need to find the CVE to fix. If anyone here wants to help, they would need to find the new CVE to fix. Probably they would go to the security tracker to find one. And then they need to confirm impact. Let's make sure that Debian, the binary patch is really impacted by that vulnerability. And then okay, I'm pretty sure that we are. So now it's time to identify the fix. Which commit is introducing that feature? Which one is fixing that feature? Let's see. How can I apply that patch on the older version? And then probably you have to modify that patch because code change a lot. So you have to modify the patch to work with that older version. And then you have to document those changes because someone else will look at it and see, what is this guy doing? Why did he do that? And so if you are going to work with someone else, like you are not the maintainer of the package, but you want to fix that CVE, you are probably going to ask for a review. So it's important for us to review the backporting changes to see if it's maybe someone missed something, maybe not. We have to review it. And then we have to test those changes because, yeah, it looks to me on paper, or actually on the screen, but does it work? Did I introduce a regression? Did I introduce another CVE in there, another vulnerability? So we have to be very careful about that. And then you can submit the fixed package. If it's going through the security team, you have to coordinate with them. If it's going to the proposed updates, which is for CVEs that don't have a DSA attached to it, you need to submit to the proposed updates. And when Debian makes a new point release, those changes and fixes are going to be distributed to everyone. And you have to watch for regressions because maybe you introduce something that broke some people random program, and then you have to be careful about that. And now I'm going to go for tips and examples of what we do. Does anyone have a question about all this that I've talked about?
Just one question. When
Yes.
you fix a CVE, that package goes back to unstable testing branches, or?
No, I did showed here that a lot of things. Okay, so we usually upload new packages to unstable, and then they migrate to testing, and at some point in time they are going to be released as a stable version.
Our stable versions actually are not completely fixed in time. So we have some options here. From time to time, for stable, for every 2 months, we do make a new point release. So every package that is on the proposed updates feed migrates to the stable feed. So everyone would get those fixes. Roughly 2 to 2 months. We can also go through the security. So we do have a feed that is called bookworm-security. So everything that's released as a DSA and a package fix through the security team goes to that feed. So I should have started. We have the stable feed, which is the main Debian stable feed. We do have 2 additional feeds. We have the proposed updates one, and this feed, the proposed updates every 2 months, get merged in the stable feed. Okay, and we have the security stable security feed, which, if you have it enabled, as soon as a package reach the stable feed, it's going to be installed in your package on your system. If you do the apt update and apt upgrade, obviously. So security fixes, as soon as they hit the mirrors, they will be available to you. Proposed updates, so minor fixes to CVEs every 2 months if you don't have that feed available. Because you can enable the proposed updates feeds on your system, and then you would get as soon as it's released.
So the proposed update have the new versions and
fixes, also some bug fixes in general. And there are some packages that bypass that because, like the kernel, every LTS release you get a lot of fixes. So the security team has that job to take care of those special packages. That's the kernel for obvious reasons. Firefox and Chromium too, they mainly get new releases uploaded to stable, even though we shouldn't mess with stable browsers. So, some tips about the evaluation phase. If you're going to go to a CV and try to understand, really try to understand it. Understand why it's a vulnerability. Understand the code. Understand the fix. Because in that way you can do a better job, like backporting it. It's always good to read external discussion. You have the OSS security on OpenWall. I think the distro at OpenWall is also released after the embargo time, so you can check that too. You can discuss with other people. You have to be careful because does that vulnerability only affects a package if a feature is on? Okay, I have to be careful because maybe I don't enable that feature, so you have to evaluate that too. Maybe, usually on Debian, I'm pretty sure that Red Hat, we all build with hardening options. So maybe you would get like information disclosure from a vulnerability, but then if you have a hardening enabled, the system will just crash, and then maybe the information disclosure becomes just a denial of service because, yeah, thankfully we have those hardening features. I have to be pretty careful on what Debian releases are affected by that vulnerability, which package versions are. Make sure that you are certain that, for instance, old stable is not affected before ruling that out. And maybe that CVE was introduced by another CVE correction. And then maybe that CVE, the first one, was backported to like Debian old stable. And if you look at the package versions from the upstream CVE details, old stable is not affected. But then you backported that fix to old stable. So you introduce the vulnerability there. So you have to be careful of those things. Maybe, we have those beautiful things called Golang and Rust that build from source everything, statically linking stuff. So you might have many places that library. So you have to make sure that that code is not bundled everywhere. So yeah, it's painful. Don't trust the CV description. Always verify it, because maybe that information is not as accurate as you'd like. About identifying the fix, have any other distro fix it already? Grab that fix if they do. So verify if they modified the patch. Why did they modify the patch on their system? Maybe it's a Fedora-specific modification. Maybe it's universal and we should get it too. So be careful with those things. Recent fixes might have hidden regressions, so if someone else applied that fix before you, check if they didn't introduce any regressions. Be careful with behavior changes, so introducing of operation limits, for instance, how many, the size of the header is someone could use the size of the header as a denial of service for curl, and then the curl upstream introduced a new size limit, and then you backported that change to dev and stable, and then someone will get in complaining, why did you do that? You broke my application. So yeah, be careful with those things. Features being removed, it's always a pain for stable backporting. Applying the patches. If you're using, I don't know, maybe VS Code or something, your editor might change that patch and it's going to be a mess, because then you are trying to review that against the pristine patch, like the commit from the upstream, and then you are like, everything is different. Why is that? Because your VS Code like changes spaces to tabs, and then everything went to, blow up. Ideally, that's a thing that we do for our backporting, Samuel and me too. We split the cherry pick of the commit and the backporting change, because then you have like a paper trail of the changes that you made to the upstream commit, and then you can verify if what the person did and make sure that it's documented and all that. So it's the best practice in our opinion. And make sure the patches apply, okay, before uploading, because, yeah. So modifying the patches. The patch might need a dependency. So be careful that evaluate and assess the risk of backporting that other patch together. So be careful with those things. Usually the function types might change between versions of the software, so be careful with those. Variables being renamed, it happens, you have to be careful with that, because otherwise you're going to break the software. Introducing new upstream functions is a bit risky, because you never know if you're, like, for sure you are increasing the size of the package, and like, so be careful with those. Try to list every backporting change in your patch header, because it's going to make our lives reviewing easier. And try to do one commit exclusively for backporting that change. So let's review that backport. It's a bit messy because it might be a diff of a diff, so your brain might need to have a few minutes to adapt to it. So be careful with those. But reviewing that backporting might save the day. Maybe you missed a variable renaming or something, so be careful you do those. If you release a broken fix, you get a new CV, so congrats. Pay attention of reordering of hunks. Usually when you edit a diff, it's going to make Git or the diff program a bit crazy. And question everything. Why did you do that? Why are you backporting this? Why are you changing the return type? Whatever. So be careful with those. Test those changes. Like, does the upstream have integration tests? If it does, use it against this new backport that you did. If the upstream introduced regression testing on a later commit, remember, don't trust only the CVE things, because if the upstream introduced the regression testing on a later commit, it's not going to be on the CVE ID, description, and nothing. So you might want to get that patch too, because it's going to make sure that you are not going to break that change in a later backport, so it's good. Does other distros have tests on it? Have they already picked up that commit and fixed that vulnerability? Check those tests. In Debian, as I said before, we have auto-package tests for most of the packages. And so make sure that you are not breaking the reverse dependencies of your package. And if there is a proof of concept available, test after you apply the fix to really make sure that you fixed that. And the last thing, the monitor phase, always mention the CVE ID on the changelog because people need to know that you fixed it on that version. Make sure that you upload it to the correct feed. So propose update if it's a no DSA, and security team if it's a DSA. Watch out to the BTS for bug reports on possible regressions, that's important. Watch reverse dependency tests in all arts, because in Debian we have 9 official ones that should be supported, and we have, I think, 10 more, like, yeah, it's a lot of stuff. So make sure that you are not introducing a regression in a specific architecture. I guess that was the main idea of the talk, to give you a general idea how we do things and how, and like, so you can be able to tell, okay, I'm used Debian, I'm safe, so that's the idea. And now I'm open for questions and comments if you have time.
Yeah.
Yes.
Well, nice presentation. I saw you work mostly on the kernel package. Do you work in kernel CVs?
No, kernel CVEs are security team exclusive. I should have said that. I'm not from security team, so.
Yeah, I saw you handle most of CVs on kernel.
Yes.
Now my question was because, well, as you probably know, the kernel.org became a CNA last year.
Yes. That's the hot topic, isn't
it? They're not playing good. For instance, I saw a number, the number of CVEs from kernel.org since 1999 to last year were around 20,200 CVEs. This year, just this year, they already issued more than that.
Yeah.
So,
but the problem is that they are treating any bug
as a CVE. I know. So my question was, how is
any fix? Exactly. Sorry.
Any bug.
Not any bug. Any fix.
Don't fix that bug, and that's not going to
exactly.
Yes. Yes.
So I myself, I have my backlog simply this year skyrocketed.
Job security.
Yes, that works. I know. But anyways,
my security job.
Oh, yeah.
Anyways, my question was, how is Debian handling the workload that simply, because since you mentioned you have this running on servers, on instances, on import customers.
Basically, the security team is like importing every LTS release. So we are just grabbing all those CV fixes, bug fixes, any fixes to the Debian stable. Occasionally, I've seen they might introduce a regression or something, but then security team has to patch that. Yeah, yes.
Yeah, exactly as you said, the whole backporting. Okay, so you're screwed just like us. Okay.
Yeah, we are all.
Okay, just wanted to share.
Yes, I know.
My feelings.
Any more questions?
All right, thank you very much. I do have some stuff. I just would like to say a few things. Thank you, everybody, for showing up and looking. I mean, just this one. Yes. So thank you very much, everyone, for being here, attending the conference. It was a great day, I think. Very good discussions, very good presentations. We lost the internet connection campus-wide, so there is a thunderstorm going on at Campinas right now. Not sure if you all know about that. We are without energy here in this building and inside Unicamp, but we have a generator. So, we lost the end of your presentation in the streaming, unfortunately, and the beginning of yours until I was able to connect the Wi-Fi, because the Wi-Fi is working for some reason. So, yeah, just to let you know, there will be a problem. I thought that the OBS was going to cache stuff or save locally. Yeah, it can save locally, but you have to choose. And, well, I did it, of course, because, that's not the default configuration here at IC. Anyway, so just let you know, it was great. And, see you again in the last week of August next year. Thank you very much.